Every algorithms course is different, but there are some topics that are pretty much bound to come up no matter what. So if you go and tell somebody that you took an algorithms course, there are certain things that they are going to expect that you know. For example, if you say, I've just finished taking an algorithms course, then anybody who hears that will expect that you do understand asymptotic notation. Whether you prefer to use big O or big theta, well, I suppose that might depend on the course, but certainly you need to understand asymptotic notation if you've studied algorithms. I mentioned back when we discussed asymptotic notation that there is a completely valid school of thought that the asymptotic notation that we use, like big O and big theta, has its place, but shouldn't be used as widely, for example, as we are using it in this course. And that's fine. But even if you took algorithms courses that were in that school of thought, you would know what big theta is and you would know what big O is. Whether you have that much time to spend on the more exotic flavors of asymptotic notation, whether you worry too much about little omega, well, that might depend. But certainly you would know about big O and big theta. Another topic that is bound to come up one way or another in an algorithms course, because apparently, I guess the community seems to think this is very important, maybe as a rite of passage, is the topic of a self-balancing binary search tree. In other words, most people that enter an algorithms course already know about binary search trees, and one way or another, they'll come to understand the weaknesses of binary search trees, as we have been discussing over the past 2 lectures. The fact that if all goes well, a binary search tree can give you log-in performance, but all doesn't always go well. And I suppose it's a rite of passage to learn about the ways that we can fix the binary search tree operations to force the tree to always be balanced. And that is the purpose of today's lecture. We're going to do that by studying something called a red-black tree. We're going to study a particular variant of a red-black tree. If you open up an algorithms textbook, it's likely that if it covers self-balancing binary search trees, it might have a section on both of these, but it will have a section on either a red-black tree or something called an AVL tree. There are other flavors of self-balancing binary search tree, but for one reason or other, these seem to be the ones, at least the ones that people that write algorithms textbooks seem to care about the most. I'll come back to this at the end of the lecture, but it appears to be the case as of 2025 that if you open up the code for a standard library implementation of a self-balancing binary search tree, you're probably going to find some variant of a red-black tree. Whether it's the exact variant that we're going to talk about today, I have no idea. I don't really... My free time is valuable enough that I'm not going to spend it trying to read through C++ code or C code or Java code that somebody's written for a standard library, given how much of that I already do in my day-to-day life. And so I suppose maybe that's a good argument, the fact that red-black trees show up in standard libraries, to cover them. But the reason I've chosen to cover them instead of AVL trees, I'm not going to talk about AVL trees, although they are very interesting, and they're not too difficult to understand once you've seen red-black trees and understand them. The reason I've decided to cover this variant of a self-balancing tree is that we're all set up for it. After everything we've said about 2-3 trees and all the weaknesses of regular binary search trees that we've covered, we are prepared to talk about red-black trees, and it's actually a pretty important topic to me, I guess for personal reasons, that we see red-black trees in a way that I guess is understandable. Because back when I was a student and I was learning about self-balancing binary search trees, they were presented as a sort of rite of passage, in a sort of, I don't know, maybe creepy gatekeeping way. That is, it was, oh, if you don't know about self-balancing binary search trees, if you can't wrap your head around these things, well, then maybe you're not cut out for this field. Which we understand in 2025 is sort of, I don't know, icky to say things or imply things like that. But even the books that were used sort of implied that. They sort of made the case that if you're a real computer scientist, then you'll be able to make short work of this. And to be honest, when I first saw self-balancing binary search trees like AVL trees and red-black trees, I was intimidated. Even after going to lectures and doing assignments and, passing the exam, I still didn't really feel like I understood them. And whenever they came up in some future course, I would sort of shift in my seat and hope that nobody would expect me to remember how they worked. And I don't know what happened. Looking back, I have a feeling that I never really learned them at all. I have a feeling that I was able to do just enough to complete exercises, but I never really understood them back then. I'd like to say, I do understand them now, many years later, after having reached the point where, I have to teach them to other people. And I look back and I wonder why that was. And I feel like one of the reasons was that when they were presented, so when I learned about red-black trees and AVL trees, they were presented in the form of, here are some slides describing operations. Here's how we do an insertion. Here are the things we do during a removal. Okay, great. Now you know about this stuff. Now you can become an expert. And looking back, that was That was wrong. That was a bit of a travesty, because we know by now, having discussed algorithms all this time, that it isn't sufficient to say, here's the pseudocode, go nuts. That isn't enough to understand it. That is sort of, I don't know, like a dereliction of duty if your job is to teach this stuff. And so I look back and I wonder whether maybe the reason for that was some sort of gatekeeping, like, oh, here are the operations. If these don't just make sense to you, then I guess you're just not good enough. And, that's not cool. If you're a teacher, that's not really the way things should work. But I also think, after having taught computer science for a while, I sort of think maybe the reason that it was presented that way, the reason that I was so intimidated by the subject as a student, might have been that the people teaching me were intimidated as well. It is reasonably well understood in the field of education that if you have a lot of anxiety about a topic and you try and teach that topic, then even if you do a good job, that is, even if you present the topic in a reasonable way, students will pick up on the fact that you're sort of uneasy about it, and they will carry that fear with them as well. And so they'll inherit it from you. When I started teaching algorithms, I thought a lot about that. I thought, are there some aspects of algorithms that I am sort of uneasy about? And when I go to present them, it'll come on, like it'll rub off on the students. Or, at minimum, will they pick up on it and think that I'm sort of an idiot, that I won't really understand what I'm talking about? And it's true that those topics actually do exist. The ones that I would say I was the most uneasy with way back when I started teaching are actually topics we've already covered in this course. My favorite material, the material with which I was always the most comfortable, is actually still coming up. In a sense, I've saved it for last. But this is something where, until I began teaching, it really was the case that although I could, bluff my way through writing an implementation of a red-black tree or an AVL tree, deep down I was sort of uncomfortable with it. And it's really important to me that we fix that problem. And so the number one thing that I think we need to do in this lecture is make sure that the operations that we describe for red-black trees are put in the proper context. I'm still, as you can tell by this, long rant I've gone on, I'm still sort of irritated by this idea that there are people out there presenting red-black trees or other data structures in a way that amounts to, here is the code, or here is a high-level description of what you need to do without any explanation of why it works or how it works or who came up with it or why. And if you don't understand this, then I guess you're just not cut out for algorithms. That isn't the way it works. That is stupid. That is not the right way to teach anything. Now, okay, so that said, now that I've vented a little bit about that, let's talk about red-black trees. So remember that we're talking about this dictionary data structure, which has these three operations: insert, find, and remove. And our goal is to store some collection of things identifiable by some key K. And for the sake of the last few lectures, we have only been considering cases where the keys are arbitrary comparable objects. So we have to organize our collection using information that we get from this comparison operation. We've seen already that the standard binary search tree structure does have these linear worst cases, but that they're pretty easy to identify. So we get this linear complexity in cases where the height of the tree is too large given the number of nodes. So the height of the tree approaches the number of nodes. And that happens if the tree becomes unbalanced. If it leans too far to one side and we don't get the benefits of the binary search operation, where we're able to ideally cut our input size in half every time we make a comparison. We've also seen that there is a remedy to this. I can create a search tree that gives me guaranteed login performance on all operations. So the example is a 2-3 tree. There are other examples of that. And the reason we covered 2-3 trees when we did is because they're going to feed directly into our coverage of red-black trees. The problem with 2-3 trees is that they have a lot of overhead. There are these different types of nodes that we have to juggle, 2 nodes and 3 nodes. And sometimes we have to condense a 3 node down into a 2 node or expand a 2 node to become a 3 node. And when that happens, that's a lot of extra cases that we have to write in code. So although we're getting login performance asymptotically, there's a big constant sitting in front of that, a lot of juggling and fumbling that we have to do to attend to all the cases for insertion and removal. And we can't avoid all of that, but certainly having 2 different node types and having to add extra code to figure out what kind of node we're working with, deal with the different keys in a 3 node, worry about the fact that some nodes have 3 subtrees and some nodes have 2, that does add up over time. And it results in implementation that's a bit bloated, that doesn't give us the streamlined performance that we want. What we want is the streamlined search operation of a binary search tree, the original recipe binary search tree, except some way of guaranteeing that if I insert or remove, I end up with a balanced tree. Remember that we've been working with this idea, I don't know what to call it, we'll call it a precept, that in a dictionary structure with insert, find, and remove, the find operation is sort of more important. That is, I am willing to make some sacrifices on the insert and remove front if it means that the find operation can be as fast as possible. Because although it is the case that there could be uses of dictionaries where I just insert and remove, it seems like this is the defining operation, and so I should optimize my data structures for the find operation. So, and then I have to, the same thing as I've had to say in the last two lectures, here is a disclaimer that points out that obviously there are applications where find may not be as important. But remember that even if you're only going to do insertion and removal for some reason, we actually need to use the find operation as part of the insert and remove operations if we're working with trees. This statement only applies to trees. I guess that should have been more clear. But of course, in a typical dictionary implementation, we might use a tree, we might use some sorted list or sorted array, and in those cases, we need to use a find operation as a component of insert and remove. However, theoretically at least, it may not be necessary to perform find as a step in insert or remove, although you have to think pretty carefully to come up with an example where that's the case. So even in cases where I don't actually intend to run any find operations myself, making the find operation as fast and streamlined as possible will still give me benefits for both insert and remove. So I guess that's an argument that even if we can't do better than log n, and we've seen already that there's a lot of evidence that we can't. To find a data structure with worst case log n in all cases or better than log n is pretty unlikely. The fact that we even have log n is pretty good. I guess my point is that if there is some way of improving a 2-3 tree or getting a similar result with less overhead, so still getting log n performance but with less overhead, it's worth it. Because binary search trees and the dictionary structure are just so important, this is an example of a case where it would be useful to investigate whether there's a way of reducing the overhead we would see in a 2-3 tree. So the question then is, can we adapt the logic of a 2-3 tree? Because we noticed last time that the flexibility we get using a 2-3 tree, that is the ability to expand a node for the node to have some elasticity to contain up to 2 keys if we need it to, does enable a bunch of operations that bring us to log n performance. In particular, we can force the tree to always be balanced by ensuring that when I perform an insertion and the height of the tree changes, the height always changes at the top. And so that is the height of all nodes is modified at once instead of the localized height increase that happens if I use a vanilla binary search tree. So we notice that by adding some elasticity to our nodes, we're able to define search tree operations that solve that problem that we saw with binary search trees where the tree becomes unbalanced. My question is it really necessary to have 2 nodes and 3 nodes to realize that? Now that I know about these operations, this clever way of performing insertion and removal such that we sort of push the problem upwards in the tree as a way of ensuring that the change that we make to height is global. Now that we know about this, is there some way of reverse engineering it so that we can use an ordinary binary search tree, a binary tree with only one type of node, and still get all the benefits we get with the 2-3 tree operations? And the answer, it turns out, is yes, we can. We just have to find some way of deconstructing a 2-3 tree, taking it apart and putting it back together, such that what we end up with is an ordinary binary tree. Maybe it's a binary tree with a few bells and whistles, but it still can have just regular 2 nodes in every position. So there are no 3 nodes. There might be something that we use to imitate a 3 node, but we do it with ordinary binary tree nodes. All right, so let's think about that. So if I'm lucky enough and I have a regular binary search tree that is a full binary tree, so here's a binary search tree which is a full binary tree, notice that that actually is a 2-3 tree automatically. It just corresponds to a 2-3 tree where every node is a 2 node. Okay, so that's nice, but of course we can't expect that because there's plenty of binary search trees that are not full binary trees. And if we attempted to view this thing, if I delete the key 72 like that, if we attempt to view the tree currently displayed as a 2-3 tree, we're in trouble because some of the constraints of my 2-3 tree aren't met. For example, the degree constraint. The node containing 70 is supposed to be a 2 node, but it doesn't have 2 children. That means this is not a 2-3 tree. Similarly, if I do something like this, I also don't have a 2-3 tree because I'm violating the leaf depth constraint, because this node is now a leaf and it is at a different depth than certain other leaves of the tree. And so we can actually argue that if we have a 2-3 tree that contains only 2 nodes, so now let's look at the same tree again, and suppose I told you actually this was already a 2-3 tree, all of the nodes are 2 nodes. Well, it's true that if I just pretended this was already a binary search tree, it would be such, because if all of our nodes are 2 nodes, then we actually have a binary search tree. So there is, if we don't have those exotic 3 nodes lying around, there is a correspondence between 2-3 trees and binary search trees, although it goes more in one direction than the other. If I have a 2-3 tree with only 2 nodes, it is always a binary search tree. It is not true that every binary search tree is automatically a 2-3 tree with only 2 nodes, because there are constraints of 2-3 trees that don't apply to binary search trees. So I guess then my idea is, it sounds like it's easy if I have 2 nodes to view them as being binary search tree nodes. I can just pretend I can just view them as if they're in a binary search tree. The problem, of course, is this. This 3 node is not something I could find in a typical binary search tree, and I guess what I want to do is find some way of converting it. Is there some way to convert 3 nodes to 2 nodes? And ideally, I want this to be reversible. The reason I want it to be reversible is if I can come up with some special flavor of binary search tree that I can convert to and from a 2-3 tree, that is, I can put it in a 1-to-1 correspondence with the 2-3 trees, then I could use all of my 2-3 tree operations directly on my binary search tree. And I need a reverse conversion for that. Just being able to turn a 2-3 tree into a binary search tree isn't enough, because I want to look at my binary search tree at any time and be able to apply the same logic I apply to a 2-3 tree to my binary search tree. So what I want is, I consider the main obstacle to be 3 nodes. I want some way to convert 3 nodes into 2 nodes, and once I've done that, to reverse that conversion. So, I don't know, to tag the nodes that I create in such a way that allows me to convert backwards if I need to. I want to do this without otherwise altering the structure of the tree. In other words, the 2-3 tree constraints are still met once I take into account the conversion. Then what I could do is store my 2-3 tree as a binary search tree. So I could use the regular binary search tree find procedure, and if I wanted to do insertion and removal, I could leverage the fact that the conversion is bidirectional to just apply the 2-3 logic directly. Okay, there's a lot, I've just said a lot there, and it may not sink in that much until we see some examples. So I want to go through examples of that. I'm going to introduce my conversion, and I feel like this is the kind of conversion that does make sense on the surface, but why it achieves this goal, given how long the statement of the goal actually is, why it achieves this goal is something we'll need some time to unpack. All right, so I think, okay, in a 3 node in my 2-3 tree, I've got 2 keys and 3 subtrees. And I wonder, is there a way of getting the same structure in any configuration in a binary search tree? And I realize, well, what I could do is I could break the 2-3 node up, or the 3 node up into 2 nodes in a binary search tree that looks sort of like this. I could create this configuration. Notice that this does give me the same in-order traversal. If I use this little construction in place of my 3 node, it obviously uses only 2 nodes and not 3 nodes. I guess it's true it's not always reversible. That is, if I just give you an arbitrary binary search tree, how do you know when you see a configuration like this, a parent-child configuration, that it was originally a 3 node? If I were to produce the thing on the right from the thing on the left, it's pretty obvious what I do if I want to go from left to right, but how do I know when I'm allowed to go from right to left? And I'll try and contextualize that. So the goal that we have in this lecture is to find a data structure that is always represented only as a binary search tree. Maybe behind the scenes, the binary search tree corresponds to some 2-3 tree, but we want our representation to only be a binary tree representation. That is, this is something that's going on in our heads, not something that's actually happening in our data structure. So we want to leverage what we know about 2-3 trees, but we don't ever want to actually store 3 nodes or 2-3 style 2 nodes. We just want to store regular binary search tree nodes. And the idea is, if we use an internal model where we're working with a 2-3 tree, that means we should be allowed to convert our 2-3 tree operations, insertion and removal, just to use them directly on the binary search tree representation. Okay, so as I said, the idea behind the conversion is that it's pretty easy to perform the forward conversion. That is, if I give you one of these, you could obviously make me one of these. What I want is something reversible. I want to be able to look at my binary search tree and know the corresponding 2-3 tree that I converted to create my binary search tree initially. And although this construction works, it doesn't give me enough information to know how to convert backwards. So here's an example I think that will try and justify that. Suppose that I created this binary search tree by converting a 2-3 tree. That is, every time I saw a 3 node, I employed this translation. And of course, I left 2 nodes the way they were. My question is, can you glance at this and tell me where the 3 nodes were originally? That is, if I created this binary search tree by converting a 2-3 tree, where were the 3 nodes? And there are certain things we can do, like we can deduce the positions of a few 3 nodes by working backwards from the constraints that we know applied to a 2-3 tree. But it's error prone, and it's something that we can't expect to work in general, and certainly not something that we can expect to write code to be able to do. That is, even if I can do it using my human reasoning ability, that doesn't necessarily mean that I can write a fast algorithm to figure it out for me, or that I'd want to. That is, even if an algorithm exists, it might be incredibly complicated. It might be better to define a conversion that makes the backwards conversion a lot easier. Okay, so what do I know about this? If this was created from a 2-3 tree, that means that the 2-3 tree constraints had to have applied, which means in the 2-3 tree, the leaf depth constraint applied. And I notice this node here looks a little bit suspicious. This is a leaf of my binary search tree, but it is at a different depth than all of the other leaves in my binary search tree. And I wonder, that might be because I employed some conversion, because I know that in the 2-3 tree, all of the leaves had to be at the same depth. So what I observe is, maybe this whole thing actually originally looked like this. So it was a 3 node. Because it does look like, it does meet the pattern, like it does fit the template of this style of 3 node, where the 2 keys are distributed with the smaller key over on the left, the larger key becoming the parent on the right, and the 3 subtrees appearing like this. And so I think, if this was a 3 node, that would explain why one of the leaves ended up at a different depth. So there's 226, and there's 485. So I think, okay, this must have been a 3 node. And I can sort of work backwards from that, because I can conclude that if this thing was a 3 node, then all of the leaves of my 2-3 tree were sort of at this level here. That is, I'll just sort of map in the 3 node. There's my 3 node there. That means that the 3 leaves below it are 116, 226, and 485. And so the leaves of my 2-3 tree are actually down at level 2. They're not at level 3. And I think, okay, how can I reverse engineer the left-hand side to make that work? And one thing I could do is I could try and say, okay, how about this? Maybe these 2 nodes here are actually originally this situation. They're actually the 2 keys of a 3 node. And so the root might be something like this. So I suppose it's true that I could deduce quite a bit of information about the original 2-3 tree, but this is just detective work. This is not something I could do very methodically, and I don't really want to think about how I'd write an algorithm to figure this out. Certainly not something I could do during an insertion or removal operation. So what I'm leading up to here is that I think we need more information in our conversion. We need some way to make the conversion reversible. So as I said, maybe we could guess, and maybe it's a function of me knowing, working with 2-3 trees for so long, but maybe I could guess that these 2 things were originally 2 keys in the same 3 node. And I do that because I look at this leaf here and think it seems a little bit out of place. Okay, so I could say, fine, this appears to be a 3 node, but what about what's happening over here? And as I said, I don't think it's easy to figure this out. I think eventually I could maybe conclude that there's at least one other 3 node in my tree, because that would result in some of these leaves being pushed upwards as they seem to require. But it's hard to know where that was, and we don't even know if there's a single solution. There could be more than one answer to that question. So okay, I could eventually reverse engineer that it was this 2-3 tree. So you'll notice that if I take this 2-3 tree and I apply the conversion I described earlier, I will get this binary search tree. Fair enough. But what I want is a conversion that's easily reversible, transparently reversible, where we can just glance at the binary search tree and it's obvious to us what 2-3 tree we started with. And what I can observe there is that it does seem as if all I really need is some way of knowing which keys were paired up as part of a 3 node. So if I were to say something like, hey, the 50 and 100 used to be part of a 3 node, the 225 and 445 used to be part of a 3 node, even if I just know that, that would be enough for me to reconstruct a 2-3 tree, and I could do that at a glance. I could agree that this is a binary search tree, but if you keep in a little bit of extra information to tell me which 2 nodes were paired up, that would be enough to reconstruct the 2-3 tree. Okay, so to make the conversion more obvious, because obviously, this direction is easy, but to make it so that this direction is also easy, I could add some extra information about the conversion. Okay, so one way of doing this would be to indicate this linkage as being somehow special. That is, these two keys are tied together by some important linkage that means that they're part of a three-node. That is sort of what I want to do, and there are some sources that define the red-black tree that we are about to discover as being related to the coloring of these edges between nodes of the tree. And that actually does make a lot of sense. The problem is that when we get down to implementing such a thing, we usually store the color that we use. We usually store this extra information that indicates this connection. We store it in a node. And so because it's just unnecessarily confusing to think about the connection being stored in an edge on the one hand and in a node on the other, I'm just going to pick a side basically and use a node. So how about this? What I'll do, whenever I convert a three-node like this into a pair of different two nodes, what I will do is I will color the lower one red. And the reason that I'm doing this is I'm indicating this red node is actually just an annex to that. This is an extension of this upper parent node here because the K1 is actually meant to be part of the same node as K2, but I can't realize that in a binary search tree. So the red nodes are sort of subordinate extension nodes on the nodes above them, on their parent. I guess if we're going to be coloring nodes red, we need a second color to refer to the nodes that aren't red. And so we'll use black. So we now have what's called a red-black pair. Why did we choose red and black for our colors? I actually did discover this. This is some bit of trivia that I figured out while making these slides. So the authors, the original red-black trees were proposed in a paper from the late 1970s. And the authors were eventually asked, okay, so why red-black? Why not two other colors? And they said, look, this was at the dawn of color printing, and we wanted to choose the colors that would show up best on the printer that we had. And it turns out that the colors that would show up best, well, still, I guess, making the text visible, were red and black. So that's a very nice pragmatic decision. There is something very nice and angular about that color choice. Aesthetically, it just sort of feels right to use colors that have that stark of a contrast. So what we're working with now are nodes that have a color that helps explain their function in the underlying 2-3 tree. Because I only want to store the binary search tree, but I want to know the connection of that tree to a 2-3 tree. So a red node is always interpreted to basically be part of its parent. So if ever I see a red node like this, really I should interpret that as meaning this whole thing was a 3-node to begin with. Now, as I said a minute ago, there are some sources that describe the red property as not applying to the node, but to the linkage between nodes. So we would color this edge red. And the idea is, if an edge is colored red, the two nodes that it connects are just the same node. They're just two parts of a 3-node that's been split in half for the sake of having a binary search tree. There are reasons why this is actually a more faithful representation of the conversion. I will admit that. I will also say that I personally just don't like this convention very much. For some reason, maybe it's because I've just learned the other way and I have it stuck in my head. But we will see later a place where I have to refer back to this point, because there's one particular special case that shows up in the case where I color the nodes of my tree versus the edges that doesn't show up if I color the edges. So this will come up again, but for our purposes, we're going to color every node of our tree either red or black. And we're going to define rules directly on the color of nodes, the red nodes and the black nodes, that mimic the constraints that we would impose on our 2-3 tree. So recall that a 2-3 tree has these three characteristic constraints. It must be a search tree, that's the search tree constraint. All of the leaves must be at the same depth, that's called the leaf depth constraint. And there's what's called the degree constraint, which is that every 3-node must have either 0 or 3 children, every 2-node must have either 0 or 2 children. Now that I have this correspondence between 2-3 trees and this red-black pair, this red-black conversion, I should be able to define equivalent constraints phrased in terminology that is more natural to binary trees. Okay, so as far as red nodes and black nodes, the way I'm going to draw them is, in these slides, I will draw red nodes by shading them red. Every node that is not shaded is just going to be drawn, I guess, normally. I've made the border a bit darker, but I guess you can appreciate I can't really shade the nodes in black because that would make it hard to read what's inside them. So if it's not red, then it's a black node. All right, so then the conversion we've just produced is to convert every 3-node in a 2-3 tree to a red-black pair. And you can observe that for some reason all this time, I have always drawn my red-black pairs this way. That is, I've always made the second key, the larger key K2, the parent, and I've always made the smaller key K1, the child, and I've always made the red node the child. That's deliberate. And although there are other ways to do this, it's good to pick one way of doing it and use it consistently, because that means that when we talk about the rules that we have to implement, so how does insertion work, how does removal work, we reduce the number of possible cases. Moreover, it means that if there's less ambiguity in how the tree is structured, it's far easier to define a bidirectional conversion. I want to be able to say for every red-black pair that it corresponds to exactly one possible 3-node and vice versa. I don't want there to be multiple ways of converting a 3-node or multiple ways of going backwards from a red-black pair to a 3-node. So in this lecture, we're going to use what I'm going to call a left-leaning interpretation. There's a slide at the very end with some credits for this, and I'll also put them in the description of the video for this lecture. But I need to make sure I point out that there are plenty of red-black tree implementations out there that do not use this interpretation. And I could, if I wanted to, define the opposite interpretation, and that would be fine as well. Although actually this is a bit of a typo. This should say K1, and this should be K2 down here. So I could define a right-leaning interpretation, but I'm going to use only one of them and I'm going to stick to it. So in this lecture, I'm always going to use the left-leaning interpretation, where I convert my 3-node to and from a red-black pair, and I always put the smaller key down and to the left, and that becomes the red child, always. I never allow a red child to appear on the right. Now, during insertion and removal, red children might show up on the right temporarily, but it's my job to fix that problem. So anyway, I said I'll put credits for where I got which sources I'm using for this. The main source is actually somebody who was one of the co-inventors of red-black trees, Robert Sedgwick, back in the late 70s, who also has taken to writing algorithms textbooks in recent decades. And one of his textbooks and a paper that he wrote from about 15 years ago, or about 20 years ago, are what I've used as my primary source for the left-leaning interpretation that we're going to follow in this lecture. So there's no requirement that red-black trees always follow the left-leaning interpretation. The reason why it's beneficial to do that is if we guarantee that there's only going to be red children appearing as left children, it means that there's a direct correspondence, a one-to-one correspondence between our 3-nodes and our red-black pairs. Versus if we were allowed to have either of these two things appear, either the right-leaning version or the left-leaning version, then that means that for a particular 3-node, I have two different options of how to convert it, and that creates ambiguity. And although it doesn't hurt anything in terms of performance, it does make it very difficult to think about all the different cases, because I now have a whole bunch of different things to consider. All right, so what is a red-black tree? A red-black tree is a binary search tree where every node is colored either red or black, and which satisfies various constraints. The constraints I'm going to describe correspond directly to the constraints for a 2-3 tree. But starting now, I'm going to have although I'm going to keep drawing 2-3 trees so that we know what's going on, I'm going to talk about everything in the natural terminology of binary search trees and red-black trees. That is, I'm going to do all of my operations in the red-black tree. I'm going to talk about all of my constraints in terms of red nodes and black nodes. We're going to have a 2-3 tree that we can keep in the back of our heads. We can use the 2-3 tree to figure out what we do when we perform insertions and removals, but I want to describe the red-black tree operations in terms of the red-black tree, not in terms of the 2-3 tree. All right, so we're going to focus on left-leaning red-black trees, which have a one-to-one correspondence with 2-3 trees. That is, for every 2-3 tree, there is exactly one left-leaning red-black tree that corresponds to it, and vice versa. If I allowed a more general interpretation, where let's say I was allowed to have a red child sitting on the right, then there might be multiple different red-black trees corresponding to each 2-3 tree, which, as I said a minute ago, isn't the end of the world, but does make it a lot harder to make sure we've covered all possible cases. So in these slides, I'm just going to keep saying red-black tree, and I refer to that always means left-leaning. If I want to talk about a right-leaning one, I will say that explicitly. But from now on, I'm not going to bother saying left-leaning. I'm just going to say red-black tree. Now, out there in the world, you might find yourself working with the code for a red-black tree that isn't a left-leaning one. There are lots of implementations that don't require that red nodes appear as left children. I believe that once you know how to use a left-leaning red-black tree, it is very easy to learn any other variant. The left-leaning one, I think, is the easiest one to learn. And as I said at the very beginning, one of my biggest goals in this lecture, a sort of personal goal for me, is to make sure that we have a presentation of red-black trees where it actually is clear why the operation operations are structured the way they are. I mean, every educator wants, anybody listening to them to understand what they mean, and that's not always possible. I get it that there are times that the lectures that I give don't make any sense. But if one thing about this lecture makes sense, I want it to be where I get these operations. When I perform an insertion and I do a certain sequence of things, where am I getting that from? That is the highest priority for me, because I believe that once we understand that, once we can properly understand and appreciate the correspondence between 2-3 trees and red-black trees, then it is pretty easy to map that onto other variants of red-black trees, or to put yourself in the shoes of a designer designing a different variant of red-black tree and figure out how operations work. So the important transferable skill isn't necessarily the way that this particular tree looks. It's how did I get it? What conversion did I perform, and how did I perform it, and why did it work? That is our goal. And so I think that using left-leaning red-black trees is great for that, because it does give us a sort of, easier on-ramp to learning about red-black trees in general. Okay, so the original variant of red-black trees, or the most general one, so that is a variant where you are allowed to have red nodes appearing as both children of a black node. I know I keep talking about that red nodes are children of black nodes, and I haven't given an explanation of exactly what the constraint is, but just bear with me for a minute until we get that set up. What we'll see is that in our left-leaning version, a red node can only be the left child of a black node. In other variants, for example, ones in which red nodes can be both children or they can appear on the right, really what's happening is those are based on a correspondence between not a 2-3 tree, but a 2-3-4 tree. And we saw last time that it makes sense such a thing can exist. That is, we can define generalizations of 2-3 trees with any number of keys per node. I want to avoid that, though, because in our 2-3 trees, we did not allow this. This 4 node isn't allowed to exist. It might come into being briefly during an insertion or removal, but we're not allowed to leave it there. So we should never have a tree in a stable setting that contains a 4 node. The original variant of a red-black tree that was proposed allowed this. It was based on 2-3-4 trees. And as you can see, by our usual convention that when you see a red node, it is attached, it is part of its parent. When I see this combination of 2 red nodes with a black parent, really what I'm saying here is I've got one big node that contains 3 keys, and I want to avoid that. So that's one reason why we're going to focus on the left-leaning version. In the left-leaning version, you are not allowed to have a red child on the right, which means if you have a red child, you can only have one of them, which means the number of keys per node in the equivalent 2-3 tree is at most 2, which is good, because that means we get a direct correspondence between our 2-3 trees and red-black trees. There are performance differences. They aren't asymptotic, though. So it's true that there could be reasons why allowing this situation can result in faster code, because you have less cases to handle when you do insertion or removal. Or maybe not. We have no way of knowing that in general. It depends on things like how you write the code. The differences tend to be minor. That is, if you choose to require left-leaning versus not, you do need extra if statements and to handle a few extra cases, and in some parts of your code, and maybe handle fewer cases in other parts of your code. It might be faster one way or the other, but not by much. And moreover, as I said, if you learn the left-leaning variant and you become comfortable with it, I think it's pretty easy to generalize your knowledge to something like this, because once you know what operations you have to perform, it's pretty easy. Just like how if you know about how a 2-3 tree works, you could probably bring yourself up to speed on how a 2-3-4 tree works pretty quickly, because you know the basic flavor of the operations and you understand why they work. And so generalizing them to a higher order tree probably won't be the hardest thing in the world. Okay, so here are the constraints for our left-leaning red-black trees, and I've now demoted the term left-leaning to be in parentheses, because as of a few minutes from now, it's not even going to show up at all anymore. So here are the constraints that must hold. First constraint, this is called the degree constraint, and it's distinct from the degree constraint in a 2-3 tree, but it does actually produce the same effect. And that is that a red-black tree must be a proper binary tree. And in a proper binary tree, every node has either 0 children, so that's a node with 0 children, a leaf, or it has 2 children. It is not permitted for any node to have only one child. It has either 0 or it has 2. And I want to leave much of this discussion as an exercise, but as a quick sketch, observe that this degree constraint, because of the way our conversion works, where I convert a 3-node into this red-black pair, this degree constraint does actually correspond to the degree constraint from 2-3 trees. In a 2-3 tree, every 2-node must have 2 children or 0 children. And so here's a 2-node with 2 children. Every 3-node must have 3 children or 0 children. And by enforcing a degree constraint on my red-black tree, I'm actually getting the same effect. Notice that here's an example of this. This is a black node with no red child, which means it corresponds to a 2-node. It has 2 children. Here's another black node here. It has 0 children. Here is a red-black pair corresponding to my 3-node. And if I consider the children of the 2 of them together, there are indeed 3 of them. And so because the degree constraint applies to individual nodes, but because also I was creating my individual nodes using this conversion, I actually find that it maps on exactly to the degree constraint from 2-3 trees. Okay, the next constraint is called red nodes on the left. And this is a characteristic of our left-leaning interpretation. So we wouldn't have this constraint if we allowed this is a tautology. If I allowed red nodes to appear on the right, we wouldn't have a constraint that required them to appear on the left. I'm not in the habit of editing things out of the video, but that's a good candidate of something to delete there. Anyway, so this constraint is simply that a red node can only appear as the left child of a black node. It is not permitted for a red node to be the child of a red node, and it is not permitted for the red node to be a right child of anything. The only position where a red node is allowed is as the left child of a black node. That means if during insertion or removal we discover a case where a red node has a red child or a black node has a red right child, we have to fix it. Additionally, there's a consequence of this. Since a red node can only be a left child of something, if ever we find ourselves in a position where the root is red, then we fix it by making the root black. The root is required to be a black node. And also, no black node can have 2 red children. So I mentioned earlier, there's a distinction between how we interpret the tree versus having nodes with colors and having edges with colors. The case where the root turns red is the place where coloring nodes doesn't make very much sense. The root is not allowed to be red because the root has no parent. And the property of being a red node is a function of the relationship the node has with its parent. So the root can't be red. The root must be a black node. If we find ourselves accidentally coloring the root red during an insertion or removal, the remedy is color the root black. Just clear the color completely. The next constraint is called perfect black balance. I'm also later in the lecture going to refer to this in passing as black depth. And the idea behind the perfect black balance constraint is that if I pick any leaf, so let's say we'll choose maybe these 2 leaves here, and I count all the black nodes that I see from the leaf all the way up to the root, including the leaf and the root itself, that number must be the same for every leaf. So let's start with this one. Okay, so I'm going to count the number of black nodes I see along the path. So there's 1 here. And then 2, and then 3. So the black depth of this node is 3. I see 3 black nodes from the leaf all the way up to the root. If I start at this leaf, I also see 1, 2, 3 black nodes. And so this is described in terms of the number of nodes along any path, but I'm going to often refer to it as the black depth of the node, the number of black nodes that you see from the root all the way down to whatever node you're talking about. And this only applies to leaves. And this constraint is an analog of the leaf depth constraint in a 2-3 tree. So in a 2-3 tree, we know that every leaf has the same depth. But that can't really apply in my red-black tree because sometimes I split a 3-node into 2 nodes across 2 levels. So while this leaf here and 485, both of these 2 leaves actually had depth 2, in my 2-3 tree, one of them has depth 2 and one of them has depth 3 in my red-black tree. But if I compute the depth and I ignore red nodes, because the red node has sort of been spliced in as a way of extending my 2-node to become a 3-node, if I ignore red nodes and I count the depth only based on the black nodes that I see, well then the black depth of, this is at depth 2 of the tree, but the number of black nodes I see is 3, and then the black depth of this is 3 as well. The reason it's 3 and not 2 is just because of the way I've defined black depth to include the root. Whereas if I talk about the typical depth inside of a tree, depths typically start at 0. So the perfect black balance constraint is a way of incorporating the leaf depth constraint from 2-3 trees into a red-black tree, but taking into account the fact that in red-black trees, because of this conversion where I convert 3 nodes to red-black pairs, I won't actually literally have every leaf on the same level of the tree. Now, the exercise, which frankly I did spoil, I got ahead of myself, is to prove that if I look at the leaf depth and degree constraint for a 2-3 tree, that implies, because of the conversion, so once I take into account the conversion of 3 nodes to red-black pairs, those 2 constraints in a 2-3 tree implies the black balance and degree constraint of red-black trees. And then a second exercise, prove the opposite direction too. Prove that if I have the black balance and degree constraints of red-black trees, those imply the leaf depth and degree constraints of 2-3 trees. In other words, if I convert the red-black tree back into a 2-3 tree, those constraints will always hold. So that's a useful proof to write because it helps emphasize the true connection between the two things. That is, although we represent them in different ways, fundamentally they are actually the same structure, just represented differently. Now, as I said, because we have this great tight correspondence, because every red-black tree in our left-leaning interpretation corresponds to exactly one 2-3 tree and vice versa, if I want to learn how to perform insertions, I could do so by simply doing the insertion on the 2-3 tree and then seeing what happens with the red-black tree. Although over time, I want to be able to frame my insertions only in terms of red-black tree operations, things that are natural in the context of the red-black tree. One point I'll bring up that'll come up a few times is that another beneficial property of this correspondence is that I can leverage asymptotic results that I have for 2-3 trees. So I'll go back to this 2-3 tree because it's larger. I know, because we proved it in the last lecture, that my 2-3 tree always has log n depth, or asymptotically log n depth. And that's good because that means that operations that are big theta of h are going to be big theta of log n. I believe that because of the tight correspondence, we can basically apply that directly to a red-black tree. We don't need to write a proof, although there are proofs. So as I said, if you take a look at Sedgwick's book, there are actually proofs of this that you can read that prove it directly from scratch versus using the 2-3 tree. But basically my logic is this. The depth of a red-black tree can be at most 2 times the depth of the corresponding 2-3 tree. Because if I look at the conversion, well, 2 nodes just become 2 nodes, so nothing changes. When I convert a 2 node, the height of the result doesn't change at all. When I convert a 3 node, I add 1 to the height. That is, if I consider the red node that I have to add, that does add an extra level to my tree. But that's it, just 1 extra level. So if my 2-3 tree consists entirely of 3 nodes, then in the conversion, I'm going to have twice as many levels as I had to begin with. But that's still log n. If the height of my 2-3 tree is log n, or let's say it's c times log n, the height of my red-black tree is at most 2 times c times log n. And that's still asymptotically log n. And so we know that as long as we can keep that correspondence tight and define operations that are still big theta of h over my red-black tree, that will be enough to ensure that I get log n performance. Another great thing about the red-black tree that you may have already noticed is that the red-black tree, of course, is a binary search tree. It's got red nodes and black nodes, but for the sake of actually performing the binary search tree search operation, I don't care about the color of the node. If I go searching for, let's say, 116 in this tree, well, 116 is greater than 100, so I go right. It's less than 445, so I go left. It's less than 225, so I go left. I can still perform my normal binary search tree find operation in the red-black tree, because the red-black tree is just a binary search tree with extra colors. So what I want to do as far as defining insertion and removal is find a way of mapping on my 2-3 tree operations to the red-black tree case. And of course, I keep saying I'm going to use the 2-3 tree for this, and that's a good idea. And on an exam or whatever, if I say insert into a red-black tree, you are welcome to draw yourself a 2-3 tree to use as a guide. I mean, there is a correspondence. They're just 2 representations of the same thing. However, in this lecture, I want to describe the operations as much as I can in terms of what I do with the red-black tree. Because if I go to write code for this, I don't want to have to convert to a 2-3 tree, perform the operation, and convert back. That's going to take forever. It's not going to give me the fast algorithms I want, and even if it were log n, which it isn't to do the full conversion, it would still have a huge amount of overhead. I want to do operations, efficient operations in the red-black tree itself. One thing, a startling thing we're going to figure out about halfway into this process is that it turns out the operations are actually easier in the red-black tree. That is, all that stuff we had from last time where we're splitting nodes and collapsing 3 nodes into 2 nodes, or splitting a 4 node into a bunch of 2 nodes, that stuff is actually way easier if I do it directly in the red-black tree than if I do it inside the 2-3 tree. Okay, this is the slide where I was supposed to make that revelation. Because basically the reason for this, the reason it's easier in the red-black tree is that the set of nodes I'm working with are just these 2 nodes. There's some 2 nodes are red, some 2 nodes are black, but the only variables I have to play with are the arrangement of children and the color of the node, versus in a 2-3 tree where I have different types of nodes, and I have the arrangement of the keys inside of the node. I can get 4 nodes by accident and have to split them. And so in the red-black tree, I end up with very streamlined operations once I'm done. So in our examples that I'm about to do, I will show the the 2-3 tree for the sake of having the context so that you agree with what I'm doing, but I'm going to describe the operation and perform the operation in the red-black tree. Now, I have to do a couple of other things on the way there to generalize the conversion, because we have discussed a one-to-one correspondence between red-black trees and 2-3 trees, and that still holds. This red-black tree corresponds to this 2-3 tree and only this 2-3 tree, and this 2-3 tree corresponds to only this red-black tree. However, we saw last time that there are some weird things that can happen during insertion and removal into a 2-3 tree where the constraints are temporarily violated. So for example, if I insert the key 3 into this, I end up with a 4 node temporarily. And we do need some way of thinking about what a 4 node looks like if we do the red-black conversion, so that we can be sure that we are performing the correct operation. Similarly, there were weird cases last time where I end up with 1 nodes showing up in my 2-3 tree during removal. I need some way of understanding what that means in the red-black tree as well. So I have to generalize my conversion a bit for that. Okay, so remember, in any red-black tree, when I think of the underlying 2-3 tree, whenever I have a red node, that red node is really just part of its parent. I mean, yes, it's a separate node of my binary tree, but by coloring it red, what I'm saying is that it is attached to its parent. It is an annex to the parent node. They are just one big node as far as a 2-3 tree is concerned, and that applies absolutely. So even if I end up temporarily with red nodes where they aren't supposed to be, I need to adopt that convention. So for example, if I end up with this situation where I have, so I'm drawing in red, but just to be clear, this is a red node. If I have a red 15 as the right child, we know that that's not allowed in general. But if it shows up temporarily, I must interpret that to mean that what I actually have is a 4 node. So a red node is always part of its parent. If that means the parent has too many keys, well then so be it. That's a problem I have to fix, but it is still the case. Similarly, if I end up temporarily with a red node attached to a red node, like this situation here, suppose I have a red 7 below the 6. Okay, so I just said a red node is part of its parent. Okay, so that means that the 7 is part of the 6. Well, how does that work? Well, the 7 and the 6 are both part of whatever black node is above them. So I go all the way up until I find a black node, and every red node I see along the way is part of that black node as far as I'm concerned. So if I see a red 7 below the 6, really what I'm looking at is another type of 4 node. It's a 4 node similar to before, just one that's been rearranged into a sort of unpleasant configuration like this. So a red node's key is always part of its parent, and if its parent happens to be red temporarily, because of course it can't be that in general, if its parent happens to be red temporarily, then I just keep going up until I find a black node. The black node is in control of all the red nodes directly below it. It is the supervising node for all the red nodes below it. All the red nodes below it are just sort of extras, extensions on that black node. So, if during an insertion or removal, I find a node with 2 red children, really what I'm seeing is a 4 node. I'm really seeing a single node that contains 3 keys. And so notice that even if I have subtrees, everything still works. That is, if I have a 4 node, I should expect that it has up to 4 subtrees, or it should have 4 non-trivial subtrees if any of them are non-trivial. It still works. If I have 2 red children, then between them, they will have 4 children to account for. So everything still works there. This configuration wouldn't be allowed in a red-black tree when I'm done, but it could show up during insertion or removal. If I see a configuration like this is also just a for node. So as I said a minute ago, if I see a red node, I walk upwards until I find the nearest black node, and that red node's key is part of that black node. And if that means I have a for node, then so be it. In the course of our insertions and removal, we will never see a 5 node. So it may be the case that we end up with a red node like this that temporarily creates a for node, but only one at a time. During a single insertion, we'll never end up with a weird situation where we've got a black node with 2 red children, where one of the red children also has a red child. That will not happen. So we only have to consider the cases where we end up with enough keys to create a 4 node, not keys to create like a 5 node or a 6 node or something. Notice that even in this unusual looking for node, we still have all the subtrees we would expect. So there are still 4 subtrees to work with, and they are positioned where we would think they're supposed to be. So the subtree to the left of the 6 is a subtree where everything is less than any key in the for node. The subtree between the 6 and the 10 is the subtree that would go between the 6 and the 10 in the for node, and so on. And so, in general, no matter how we arrange those red nodes, any subtree that consists of a black node with 2 red descendants, 2 direct red descendants, will have 4 subtrees. It doesn't matter if it goes left and then left, or left and then right, or right and then right, or right and then left, whatever. It's always going to have 4 subtrees, and therefore, no matter how they're arranged, we do still just have a for node here, which means that the way we remedy it is the same as we would remedy any for node in a 2-3 tree. So we know already that in an insertion, if we get this situation, we fix it by promoting the 10 to go up and then peeling off the 6 to one side and the 17 to another, and then just stealing 2 of the subtrees, having each of them steal 2 subtrees. So the same thing is going to hold in our red-black conversion. Now, you'll notice that in these temporary configurations, so these can all show up during insertion, but it's our responsibility to get rid of them by the time the insertion is done, that these are all ways of representing the same for node. So although I drew a bunch of different examples, the ones in the slides, if you look at them, here's the for node I get for this situation. Here's the for node I get for this situation. It's the same one. And then here's the for node I get for this situation here. It's exactly the same for node. So these are cases where some of my constraints are not met. So this is the case where the constraint where the red node has to be a direct child of a black node is not met. And here's the situation where the red node is a right child not being met. Here's another situation where the red node is a right child, which is also not allowed. If I were to allow red nodes to be right children, then there would be lots of different ways of representing exactly the same 2-3 tree, which would become a bit of a headache. And that's one of the reasons we have that red on the left requirement, as the slide is pointing out, is to eliminate the large number of equivalent configurations. So once I'm done my insertion or removal, there is exactly 1 2-3 tree for every red-black tree and vice versa. Okay, so during insertion and removal, we may encounter these configurations that are not allowed. So nodes that have 2 red children, like this situation, or nodes with 2 red descendants over on the right, or with 1 red descendant on the right. And we have to figure out a way, before we get into the actual insertion and removals themselves, of remedying that using binary tree operations only. And so there is this one important binary tree operation. It isn't specific to red-black trees, although we're going to use it in red-black trees, I think only. I can't think of the next case where we're going to need this operation. It's something called a rotation. It's an operation you can apply to any binary tree, but it's very helpful for rearranging the children of a node in a red-black tree to produce a configuration that is permitted. We're also going to have to modify the color of nodes in certain cases to eliminate configurations that make no sense. So the 2 tools that we will use, and it turns out these are the only 2 tools we need in general for red-black tree insertions and removals, are called rotations and color flips. So a rotation rearranges the subtrees of a particular node by shifting them over. And we can think of the reason it's called rotation is, so consider this situation here. I have a subtree, so it could be buried inside of a larger tree, and it's rooted at K1. I could observe, hey, this subtree looks a little bit like it leans too far to the right. What I'm going to do is I'm going to rotate it by just pulling everything up and to the left so that K2 becomes the root and K1 hangs off of K2. Now to actually do this, I also have to rearrange the subtree. So if I want to pull K2 upwards and have it become the root, okay, so I've got K2. I have this subtree T2 that consists of values that are greater than K1 and less than K2. Because K2 is now the root, I guess K1 gets demoted to become the left child of K2. The subtree T1, which is stuff less than K1, that can still go over to the left. The subtree T2 only really has one place it could go. Now that K1 is a child of K2, T2 has to get slotted in as the right child of K1. And then finally, K3 gets pulled upwards pretty much intact, so its subtrees are still where you expect them to be. Now I realize this sketch looks pretty illegible, but I'm just sketching the same thing that we see on the right. So what I've done here is a left rotation about K1. I've pulled everything up and over to the left about around the node K1. So K1 gets pushed downwards and K2 gets moved up. And so that's the general term left rotation in any binary tree, is where I take a node and I push it downwards and to the left, and I pull its right child up to become the new root of the subtree, and then I rearrange subtrees in the only way that makes sense. That is, once I've done this, once I've pulled K2 up and pushed K1 down, there are really only 4 places the subtrees can go that make any sense. So that's a left rotation. And then here's an example of a right rotation. So I have K3 is now the root of my subtree, and I pull everything up and to the right, and K3 gets pushed down, and I end up with this tree here. So this is a right rotation about K3. Now, rotations can be performed in any binary tree. That is, that's an operation that's independent of the idea of a red-black tree. However, notice that in both of my previous examples of rotations, the thing I was rotating was basically a for node. And the reason is because we use rotations as a way of getting rid of this problem where a for node is leaning too far down to the right. We don't like for nodes, but it's way easier to deal with for nodes when they look like this. When we have a black node and its 2 immediate children are the 2 other keys of the for node. So although rotations can be performed in any binary tree, not just a red-black tree, when I use rotations in these slides, I will also do a subtle color rearrangement. So when I performed, so here I'm performing a right rotation. Notice that when I'm done the right rotation, I started with a black node at the root. When I'm done the right rotation, I started with 1 black node and 2 red, but when I'm done the rotation, I still have a black node at the root, and I've colored K1 red. That isn't really part of a rotation. So this is one aspect when I've looked at diagrams of other people's red-black tree stuff that they sort of leave out. So I've added this slide to make this clear. This isn't magic. This isn't part of the rotation itself. It is something I'm choosing to do as housekeeping when I do the rotation. Like after doing the rotation, I do this. So whenever I perform a rotation, it is customary in this context to also modify colors to sort of rebalance the colors. Although the actual color modification I need to do, the main color modification, I'm going to get to in just a minute. So you'll notice that when I perform these rotations, when I have these 2 red descendants, once I'm done, the root node that I end up with is still a black node. And I may have also colored some other node red, so I still have 2 red descendants. They've just been rearranged in sort of a pleasant way. So from now on, when I do rotations of for nodes, I'm just going to call this whole thing a right rotation about K1, even though actually it's both a rotation and a little bit of color shuffling to bring things back into line. So therefore, just be aware of that. That's not magic. I am giving you a disclaimer of where I'm getting that from as of now. Similarly, if I were to do a right rotation about K3, then when I'm done, K2 will be the root. So I do the rotation, but then I fix up the colors so that this black node's 2 children still are part of that node. I still have a for node just like I did to begin with. Occasionally, I end up with for nodes that look like this, so we can see here that K1, K2, and K3 are all part of the same node, because once I trace up from K2, K2 is part of the same thing as K3, so it's the same for node. However, if I want to get this thing to look like this, using rotations, I actually have to do 2 rotations. The first rotation I do is one of these. I do a left rotation about K1. And when I'm done, what I end up with looks sort of like this. So K3 and T4 are where they were to begin with, but now I have K2 here, and then K1 to its left. So I've done one of these. And then I rearrange subtrees to look like this. So after 1 step of rotation, I end up with this configuration here. And then you'll notice, so this is a red node, and this is a red node. And you'll notice this configuration is basically what I had over here on this slide. So once I'm back in this shape, I can do a right rotation about K3 to get us back to the preferred version of the for node that I want. So in this case, to turn this for node into a more pleasant shape, I have to actually do 2 rotations. I'm going to call this a double rotation. So I first do a left rotation about K1, and then I do a right rotation about K3. Notice that because of the way rotations work, they don't change anything about the ordering of the tree. And so you can see, for example, T1, when I started here, was the subtree of things less than K1 and less than everything else we can see. When I'm done, T1 is still to the left of K1. If I look at, let's do T3, T3 is the subtree that is stuff between K2 and K3. So that is to say, it would be the third of 4 subtrees for my for node. Notice that when I'm done, T3 is in exactly the same position with respect to all the other keys as it was before. I've just moved the keys around, but I haven't changed the relative ordering of either the keys or the subtrees. Also notice that over on the left, the in-order traversal of K1, K2, K3 is K1, then K2, then K3. Over on the right, it's the same. So the rotations I've done have not changed the ordering of the tree. They've held that invariant. That's important because that means that I can use rotations to fix the other constraints without worrying about breaking my search tree constraint. Okay, now color flip. Now this is actually a pretty trivial definition. It shouldn't surprise you at all. So if I perform a color flip starting at K2, so I perform a color flip of K2, what I'm referring to is that I flip the color of it and its immediate children. So once I get a for node that looks like this, I will choose to perform a color flip on it in certain cases, and we'll see the value of that once we begin doing insertions. And when I perform the color flip, I'm converting both of the children to black nodes and the parent to a red node. In general, we only do color flips when the parent is black, and then the result is the parent becoming red. We don't generally do color flips when the parent is already red. Okay, so I've talked about my tools, rotations, and color flips. Now we're ready to start modeling our insertion process. So our task is to insert the key 6 into the red-black tree above. We know how we do this in the 2-3 tree. We know that we cram 6 into this, create a for node, and then split the for node with the 5 getting propelled upwards. What I want to do is model this entirely using the terminology of a red-black tree. So the first step of the insertion process in the red-black tree is to perform a normal binary search tree insertion and have the new node I create always be red. So over in the red-black tree, I want to insert the value 6. So I do a normal binary search tree insertion. And I get down here and I discover that my insertion position is going to be this. And so I make a new node. I just do it like in any other binary search tree insertion, and I color my new node red. We can see already that this is not going to work. I mean, we're going to have to do some sort of adjustment here because this is a right child. We're not allowed to have a red node on the right. Also, once I stare at this, I notice that, yeah, this is actually going to be a for node, which is exactly what we expect. If I did the insertion in my 2-3 tree, I would have a for node. And over here, I have a for node as well. Okay, so the insertion process always begins by doing a normal binary search tree insertion, and the thing I create, which is always a leaf, is always red. Okay, so there it is. So I insert the key 6 as a red leaf. Notice that what I have, if I interpret this as a 2-3 tree, is a for node, just like I expect. Okay, so clearly we're not done the insertion because we know already that we've broken one of the constraints of my red-black tree. And on the right-hand side, we can see that our 2-3 tree's got a problem as well. We have a for node that we need to split. And in the red-black tree context, notice how the existence of the for node is sort of encapsulated. It is accounted for, I guess, by that red on the left criteria. The fact that red nodes can only be the children of black nodes and they must be left children. Because this is violated, that's a way of us knowing we actually have a for node. Okay, so what do? I need to split the for node. And to split the for node, so, I guess on the 2-3 tree, what I would be doing is I'd be pushing the 5 upwards and converting the 6 and the 4 into 2 nodes. And I end up with a 3 node up above. Okay, so that's what I have in the 2-3 tree. How do I achieve the same effect in my red-black tree? Okay, well, let's just start with pushing the 5 upwards. I want the 5 to become part of the 9, to enter into a 3 node with the 9. Currently, the 9 is a 2 node, and so is the 5. So what I want is for the 5 to become part of the, to become part of a node, the parent node, turn your node red. So I'm going to make my 5 a red node. Okay, so what I've done here is I've forced the 5 into a 3 node with the 9. Okay, that's nice. But now I also want to make the 4 and the 6 2 nodes. They get to become their own subtrees of my 3 node. So that when I'm done, I have a configuration that looks like this. How do I do that? Well, to make something into, currently the 6 and the 4 are both red, which means they're part of the node containing the 5. I want them to be free. I want to set them free as 2 nodes. So what I do is I just make them black. And I can't do that because I can only draw in red, but I just make them black nodes. So what was the operation I just performed? I made the 5 a red node, and it was a black node. I made the 2 red 4 and 6 nodes into black nodes. In other words, I just flipped the color of the 4 node. And so the splitting operation, which is a bit of a pain in a 2-3 tree because you've got this 4 node, you've got to get rid of it, you've got to create a new 3 node and replace the root with a 3 node, you've got to add the 5 to it, make a bunch of subtrees, add child pointers. I don't need to do any of that in a red-black tree. All I do is I just flip the colors, and that's it. I'm done. Because once I'm done flipping the colors, so to be clear, the operation I did was a color flip with respect to node 5. When I say color flip, I mean flipping the colors of the node and its immediate children. So I do a color flip of node 5. That turns the 4 and the 6 into black nodes, which means that they are now 2 nodes as far as the 2-3 tree is concerned. It turns the 5 into a red node, which means it's now part of the node containing the 9. And we're done. I have now done the entire 4-node split operation, adding the 5 to the node containing 9 and rearranging subtrees pretty much instantly with 3 extremely simple color flipping operations. All I did was change the color of these 2 children and the parent, and I'm done. I love this example because not only is it a good introductory insertion example, but if you weren't already convinced that we were going to get some real mileage out of this conversion, I think you are now. Because in the 2-3 tree, if you had to write code for that split, it would be a bit of a pain. In the red-black tree, it is absolutely easy. Okay. So remember, the color flip only works to do this split operation in the case where it looks like what we had before. So we've seen that there are other ways our 4 node could be structured. That is, I could have a 4 node that looks like this. So the 6 is black, the 4 is red, and the 5 is also red. This is the same 4 node that I have otherwise. The problem is a color flip at the 6 wouldn't fix the problem. The only time I can fix the problem with a color flip is if I've arranged the 4 node like this. And you saw a few slides ago, I kept doing rotations to try and put 4 nodes into this form, and that's why. I have to rotate the 4 node around until it looks like this, until I've got a black node with 2 red children. Then I do the color flip to model the split operation. Okay, so that means if I encounter a case where I've got red children that hang down in some other configuration, I have to rearrange the red children until I get them into the configuration I had a minute ago. Okay, so I'm now done the insertion. All I did was add a new leaf and then walk my way up the tree checking for violations. And when I found a violation, so the violation I found was here. This is the node where I would consider, this is the node that's to blame for this situation because the black node is responsible for its children. I fixed the violation and no further violations exist, and so the insertion is complete. All right, let's insert the key 10 into this red-black tree. So remember that the first step of insertion is always to do a normal binary search tree insertion, and that would end up here. And the new leaf is always red, so we end up with this. Now, this creates a 4 node, of course. It is not a 4 node in the most convenient representation. So here, 18 owns these other 2 keys that go down left and then left. If I want to use my color flip trick, I have to first rearrange them so that so I have a black node with 2 red children. And the solution to this is to perform a rotation. So what I want to do here is I want to rotate right about 18. So 18 gets sent downwards, 12 comes up, and 10 becomes the left child. When I do this, I'm also going to do that the recoloring that I mentioned before. I'm going to keep the root of my rotation to be black, and I'm going to make both of its children red, because I know that what I'm ultimately doing is just rearranging the elements of a 4 node. So right rotation about 18, so I end up with this configuration here. Okay, so now I have a 4 node that I can split using a color flip. So if I do a color flip, the 10 will become a black node, the 18 will become a black node, and the 12 will turn red, which means the 12 is now part of the parent node. So I do that. Now, unfortunately here, by doing this color flip, although I did solve the problem at the lowest level, of course, I now have a 4 node up here. So now the 9, 5, and 12 are all part of the same thing, but also the 12 is a red right child, which I also am not allowed to have. And so I look at the 2-3 tree and I observe that it's pretty clear how I would fix this problem in the 2-3 tree. In the 2-3 tree, I would send the 9 upwards to become the new root. I would take the 5 and it would become the left child, and it would steal these 2 subtrees here. I would take the 12 to become the right child, and it would steal the other 2 subtrees. So I would split this 4 node with the same logic I usually use. I have a 4 node in the red-black tree that is structured perfectly for a color flip. So I could split it with a color flip, although then I have one contingency I have to clean up. So it's a 4 node, I split it, I do a color flip, and what I now have, well, it's sort of this, although this is a bit of an anomaly. So by doing the split, I promoted 5 and 12 to become 2 nodes, and we can see that it's reflected in my 2-3 tree, but when I flip the colors, the root turned red. And this is a bit of a problem because how can the root be red? The property of being red describes a relationship of a node to its parent, and the root has no parent. So this is the case that I alluded to earlier when I said that often when people talk about the original definition of red-black trees, and a definition that's often used by people, doesn't describe a node as being red, it describes the linkage between a node and its parent as being red, because it doesn't make sense for the root to be red. Now we're going to resolve this by simply declaring that the root is never allowed to be red, and therefore if you ever encounter a red root, you just switch it back to be black. So we can finish off our insertion by simply, I guess, ex cathedra, defining that the root will always be black. And this special case only applies to the root. So we don't worry about ever having any ex cathedra declaration that other nodes are black, only the root. If the root is accidentally red, just assume that that was a mistake and color it black. Okay, so the last step is set the root to be black. I now have a 2-3 tree and red-black tree that have been restored, and the insertion is complete. All right, let's try the insertion of 17. Okay, so in the red-black tree, that would mean I go over here and I add 17 as a red child to the 18. In the 2-3 tree, when I want to insert 17, it would be fine to just make 17 and 18 into a 3 node. So I've got 2 different ways of viewing this. Once I do the insertion, I realize that I'm actually done. So in the red-black tree, my 17 becomes the left child of 18, which is allowed. I have a 3 node that consists of 2 keys, and it happened that I inserted it on the left, so everything's good. In the 2-3 tree, that does correspond to a 3 node. So actually, I'm done the insertion. All right, great. So I was lucky enough here to do an insertion on the left of a black node. Okay, so now we'll insert 7 into my red-black tree. Okay, so 7 would have to go over here. There it is. And so I observe that really the effect of adding 7, what I want is for 7 to be part of a 3 node with the 6. But in the red-black tree insert procedure, I have to add 7 as a red leaf to the right of the 6 because that's where it goes in a binary search tree. So I end up with this. So it turns out that actually if I'm allowed to accept this as a 3 node, I actually already have a valid 2-3 tree, but I have to rearrange the red-black tree to comply with my extra constraints, to canonicalize the red-black tree, because I'm only allowed to have red children on the left. I still want this 3 node, I just have to have the 3 node arranged properly, which means that I guess what I want is for 7 to be up here and 6 to be down to its left. So 6 becomes the red node. So I can solve the problem by performing a rotation about 6, a left rotation about 6, where then I fix up the colors so that the root is still black. So I have to do a little bit more work, although this is just housekeeping to bring us in line with our definitions. We already have the correct structure of the underlying 2-3 tree. We just want to ensure that we have our left-leaning red-black tree. So I perform a left rotation about 6 to put 7 at the top and 6 below it. Notice that in the left rotation, I also did a recoloring to ensure that 7 was still a black node and 6, being the child, was the red node. And then I'm done the insertion. Okay, so that was a pretty simple case as well. It was basically insertion into a leaf from the 2-3 point of view, but I had to do a small rearrangement to bring it in line with the red-black constraints. Okay, insert 15 into this red-black tree. Okay, so I know that the 15 would go in a binary search tree insertion down here. And I can see that it would go here in my 2-3 tree, which means I am going to have to split something. I may have to do other rearrangements to get the 4 node into the right shape. All right, so I add 15 as a red leaf. This creates this 4 node here. The problem is the 4 node is not optimally positioned. It's not arranged in a way that I can work with it, so I have to do some rotations. The rotations I want, so what I want is to have this configuration here instead of what I already have. To get this, what I'm going to do is first perform a left rotation about the 12, and that's going to give me this situation here where this is 15 and then the 12 is down below it. And then I can take the whole thing and I can swing it up and around to get the 4 node configured so that a color flip is doable. Now you might be looking at this and thinking, why are we bothering with why am I talking about this using rotation terminology? Isn't it fine to just say make a new child of 18 and then rearrange the keys, like make this 15 and make this 18? Well, okay, in this case maybe yes, but I want to talk about insertion generally, and the slides are only so big. So we have to consider the case that in general there could be subtrees here. So I could have, let's call that one T4, and then down here I have T3, and then down here I have T2, and then down here I have T1. And so in the event that I end up with this configuration showing up during an insertion, I have to make sure that whatever I do to rearrange nodes preserves the ordering of subtrees, and rotations are the best way to model that. So when I do the rotation, the first part of the rotation this way, I tilt everything down and the subtrees stay in order. We already learned that when I do rotations, the order of the tree is preserved. That is why I'm insisting on talking about these operations in terms of rotations, because I'm guaranteed that rotations preserve the underlying in-order traversal of the tree. So I do a double rotation, and that's going to be first a left rotation about the 12, which gives me this situation here, followed by a right rotation about the 18. And that gives me this. Okay, so now I've got my 4 node arranged in a way that allows a color flip. So I do the color flip. Doing the color flip automatically produces this configuration here. The 15 now joins the parent, and these two things get promoted to become 2 nodes of their own. Okay, so now we already saw this case. So now in the parent, I've got 3 keys and I have to split it. So I perform a color flip again, and then I set the root to be black. Okay, so that was only a small variant on the insertion we already did. As we saw, if the root ever ends up being red, of course, that's fine. We just set the root to be black. Every other node, of course, it being red means something, but when the root is red, that's an accident, and we just set it to be black. All right, okay. So here's a wall of text. Basically, I hope that the examples I just showed give enough evidence that if we see a violation of the 2-3 constraints in the red-black tree, we can detect them pretty easily. That is, they occur by verifying that red nodes appear on the left, and that if we want to fix them, the fix will always be some combinations of rotations and color flips. There are lots of different configurations we could have to address, but all of them can be fixed by doing rotations and color flips. So an example being, we saw just now in this insertion, we had this situation. This is a 4 node, but we have to do a bit of rearrangement before we can treat it like any other 4 node. We have to put the 4 node into a sort of basic canonical form, which looks like this. And we can do that with rotations. We can detect that we have a problem by simply looking at each node and verifying that the red on the left constraint has been met. And notice that it hasn't been met here. That's how we know we've got some rearrangement needed. So in this case, the rotations we have to do are we first rotate about the 12 and then the 18. If I had the symmetric case, so suppose instead of this, I had 2 red nodes going this way, well then there is a different sequence of rotations needed. I'd have to go this way and then this way, but I could still do it. So any violation that I detect, I can solve using rotations and color flips. And the detection of the violation basically just amounts to verifying that red nodes always appear on the left, and that you never have a red node that's a child of another red node. The other constraints, so remember that there are other constraints in red-black trees. Red nodes on the left, that's one of them. There's also the degree constraint, but the degree constraint we can expect will always be satisfied because the rotations that we do don't modify the degree constraint, basically. And there's also the search tree constraint. But again, we don't need to worry too much about that either. There is the black balance constraint. And interestingly, we haven't really had to address that just yet, but we're going to have to think about that a lot more for removal. As far as I can tell, and just like with 2-3 trees, maybe this is up for debate, but there are 5 cases. We can break insertion down into 5 different cases. And what I've done, just like with 2-3 trees, is I've made a slide to sort of summarize each case theoretically, so that if you're implementing code for a red-black tree, you don't have to reverse engineer all of my examples that I just went through. There's actually separate cases for each one of them. Just like with 2-3 trees, the argument I'm going to make about running time is that the restructuring operations each, so each rotation by itself, is a constant time operation. Color flips are clearly constant time. Flipping the color of a node and its two children, that's clearly a constant time operation. There are just three things I have to change. Additionally, the restructuring itself can be performed by following a path upwards from a leaf to the top of the tree, to the root of the tree. And because at each step, the restructuring I need is at most 2 rotations and a color flip, then that means I do a constant amount of work at each step, and the number of steps I take is big theta of h. Due to the correspondence with 2-3 trees, so as I mentioned earlier, we can assert that the height of my red-black tree is at most twice the height of the corresponding 2-3 tree, which is therefore still going to be log n. The 2-3 tree has a log n height, or big theta of log n, and so my red-black tree also has a log n height. And that's enough. That's enough to verify that our red-black tree insert operations are going to be all in log n, big theta of log n. Okay, so here are our cases. Case 1. Suppose that you're somewhere in the tree. So this is something that you should be testing on your way up the tree. So just like with a 2-3 tree, we keep looking at nodes until all violations have been resolved, which does involve going into the parent and checking for violations there if we just fixed a violation at the current level. So maybe you just inserted a new leaf. And so it's K1 here. But case 1 could also apply if you find yourself elsewhere in the tree, so you're checking for violations with respect to this node here, and up from below you now have a new red child. That could happen. So a red child could have propagated its way up the tree somehow, for example by color flips. So case 1 is meant to refer to any situation where a node now has a new red left child, with no other red subtree, so the right child is not red. This is equivalent to the case where you cram in an extra key into a 2 node and you end up with a 3 node, and nothing extra is needed in this case. So when your new red child is on the left, you're good. Everything's done. Case 2. Suppose you have a new red child, but it shows up on the right. So as I said, this could be because you literally just inserted K2 as a new node, but it could also be that maybe previously K2 was a black node and it just got recolored to be red. So somehow, from the point of view of K1, you have a new right child which is red. You know that that's not allowed. And so the solution to it is to perform a rotation. So we saw this case earlier. All I have to do is arrange this 3 node so that the larger key is at the root and the smaller key is down and to the left. So I want this. And the way I get that is simply by performing a left rotation about K1. And of course, doing the color fix-up that I'm implicitly doing when I do the rotations. Okay, case 3. Suppose I have a new red right child, and I already had a red left child. You can sort of verify to yourself that if you get a new red left child, you can't already have a red right child because that means it was already there. And that doesn't make any sense because those aren't allowed. So the only time you end up with a new red child, only time you end up with 2 red children is if you get a new red right child. Okay, so I have a new red right child, and I already had a red left child, and so the solution to that is what I'm really dealing with here is a 4 node, as we can see. And the solution when I have a 4 node in this configuration is to simply perform a color flip. So I perform a color flip, so K1 and K3 now become 2 nodes, and K2 becomes incorporated into its parent, wherever that is. And so the solution is I do a color flip and then I recursively restructure from the point of view of the parent. So now my parent has a new red child and it has to go handle that. It could fall into case 2 or case 1, or it could be another case 3 situation. All right, so now I have to address the other configurations I could encounter. And so one of them is, okay, so you're at K3, and you now have a left, I'm going to call this a left-left red node. It is sort of a red grandchild over on the left, whatever. So we'll call it left-left red node. This is also a 4 node. We've already seen this configuration as well. We know the solution for a 4 node. So if my 4 node looks like this, then I just solve it by a color flip. For every other type of 4 node, basically what I want to do is rearrange it until it looks like this, so I can just use case 3. So that's what I do here. In this case, where I have a red chain that goes left-left, what I do is I just rotate right about K3. And so I end up then with this configuration. I rotate right so that K2 becomes the root, and then I recolor so that the 2 children are red. And then I've got case 3. So once I have this, I just back up and handle it like I handle case 3. All right, case 5. Suppose I have a new left-right red node. So my red grandchild is left and then right. This is also a for node, but of course I have to put it into a more convenient form before I can work with it. So here what I'm going to do is I'm just going to rearrange it just enough that I can go back to case 4. That is, we saw when we handled this that we could do double rotations. I could first rotate about K1 and then again about the root to get it in directly into case 3, but I'm lazy, so what I'm going to do here is simply describe how to get us to case 4. So what I do is I perform a left rotation about K1, and that gives me this configuration, and we can see that this is the input configuration for case number 4. And then I can just handle it accordingly and then bounce down into case number 3. There it is. That's insertion. So when it comes down to it, insertion will only ever really fall into one of these 5 cases, some of which are easy, some of which just fall into other cases, but all of them can be solved with rotations and color flips. There's no need to wrangle different types of nodes. There's no need to actually formally split nodes or merge nodes. The splitting and merging basically happens in the background as a consequence of the configuration of colors. And that's great because that means that we can now, as far as insertion is concerned, get all of the benefits of our 2-3 tree with none of the hassle of extra different node types. All we need is the ability to keep track of the color of nodes. And that's just one extra Boolean variable, pretty much. Is the node red or not? Something that we then have to flip back and forth as we walk up the tree. Okay, so now the next one is removal, and removal is going to be a bit more involved. So our task is remove the key 9 from this red-black tree. And we are going to benefit quite a bit from what we know about 2-3 trees because we know from talking about 2-3 trees last time that removal was a bit of a headache even then. Okay, so first thing we do, the very first thing in any removal is go find the thing we're going to remove. So we go find it and we delete the key. And as in the last couple of lectures, I will use this symbol to indicate that a key has gone missing. And that, of course, when I'm done, there can be none of these left in the tree. I have to eliminate all of them. But it's useful to sort of visualize the gap in the tree created by my removal. Okay, so in a 2-3 tree, we're currently doing an easy removal case. So here, we've got a 3-node leaf, and we've just removed its only key, or one of its 2 keys. It now only has 1 key left, but that's fine because it has no children, so we could just collapse it back into a 2-node. Over here, I've got a red leaf that was just deleted, and similarly, I could basically just ignore it at this point. And so in this case, it's an easy solution. I want to collapse my 3-node down into a 2-node. In the case of the 2-3 tree, that requires swapping a 3-node for a 2-node. In the case of the red-black tree, all I do is delete the red left child, and we're done. That wasn't so bad. It can't get much worse than that, right? Okay, so let's delete 10. Okay, so there's 10. I go looking for it. I go find the 10, and then I set its key to be empty. Okay, and what I have now is this empty black node, which is, okay, so last time I did distinguish between a case where a leaf was empty versus a 1-node. The slide is therefore, they shouldn't necessarily be lumped into the same case, but for our purposes, I will think about them being the same. This empty node here, this was previously a black node, so a 2-node, but it currently has nothing in it. And so it's certainly a degenerate case. And I will view it as being equivalent to one of the 1 nodes that we had to work with last time. And of course, it's our job to eliminate it before our removal is complete. What I'm going to call this thing, because we're going by color today, red and black, is this is now going to be a gray node. So a gray node is a degenerate node that does not contain any key at all. It is a black node that isn't able to fulfill its role. It does not have a key. So the gray node is a displaced black node, and that means that we can't simply delete it. The red node in our earlier example could just be deleted because it was a contingency. It was an annex to a black node. Deleting a black node is a problem because we're going to violate one of the constraints of our tree. So see, if I delete this, if I were to just simply delete it wholesale, then I end up with a bit of a problem because my degree constraint is no longer satisfied, because now 8 does not have 2 children. Same thing over here. And we saw this in 2-3 tree deletion, as it isn't as easy as deleting nodes because the global structure of the tree depends on these constraints that will be violated if we simply delete nodes. Instead, as we did with a 2-3 tree, we sort of have to push this node around a bit until either we find a key to fill it in, or it gets pushed to a place where where we can simply delete it wholesale. We saw last time that pretty much the only time we can completely delete a 1 node without filling it with a new key is by pushing it all the way to the top of the tree. That's going to be the case here as well. So what do we do in the 2-3 tree here? Well, in the 2-3 tree, we now have a family. If we look at the immediate family of the empty node, we've got 3 keys and 3 positions. And so what I could do is simply push one of the nodes from the sibling up, one of the keys from the sibling up, and then pull the key from the parent down. And I could look at how that would work inside of my red-black tree. So yes, in a 2-3 tree, I would have to collapse this down into a 2 node. I have to move this key up and make a 2 node here, and then push the 8 down. In the red-black tree, though, what is it that I want? I want the 8 to come down, the 6 to go up, and the 5 to go up, and I guess the 5 becomes a 2 node. It becomes a black node. Isn't that just a rotation? Well, yeah. So I could just do a rotation, a right rotation about 8. So I do a right rotation about 8, and I end up with this. Notice that as part of my rotation, I also change the 5 to be a black node. And then I'm done. And I can observe that my constraints are all met. One constraint that is particularly critical in the removal stage is the black balance constraint. So it's a good idea right now to verify that if I look at any node of my tree, any leaf of my tree, and I walk upwards to the root, the number of black nodes I see is the same for every leaf. So if I start here, I can see 1, 2, 3 black nodes on the way to the root. If I start here, I can see 1, 2, 3 black nodes. And you can verify that that applies for every one of the leaves of my red-black tree. All right, let's remove 92. Okay, so there's 92, so I get rid of it. It's now empty. And over in the 2-3 tree, I have reason to be hopeful because it seems like 92 is part of a pretty dense family. So it looks like there might be some keys to spare if I know what I'm doing here. Okay, so I deleted the key, and now I have this empty node. And now I have a parent 3 node with 2 subtrees and 2 keys. And what I could do is basically change the parent to a 2 node. So I don't know, I could say maybe the parent contains the 34. And then I could have one subtree that's a 2 node. I shouldn't have drawn it there. I could change the parent to a 34. One subtree is a 2 node, and the other 2 keys get jammed into a 3 node. So something like this. Okay, so that's one of my options. And I asked myself, what am I actually doing? Like if I perform that modification, what is it that I'm really doing with the keys? Okay, so I'm pushing 71 down. I realize now that actually it might be more convenient for me to say something like the 71 is over here by itself. So I need to use rotations to get this done. I'll actually need a double rotation, so I'll just show it to avoid I'm losing confidence in my drawings here. They're looking a bit sloppy. Okay, so the first thing I do is what I want to rotate this way eventually, but currently the tree isn't in good shape for doing that. So I actually have to do 2 rotations to make this possible. And I'll just walk through them and sort of work backwards from there. Okay, so the first thing I do is I perform it's not going to show them both at once. Okay, so I perform a left rotation this way. So I'm basically, by doing this, I'm pulling the entire subtree into being a sort of chain like this. This will be 34. And this will be 58. So I perform a left rotation about the 34, and then once everything is in this chain, I can just sort of hoist everything along around the 71, and I end up with this situation here. And I realize now that the example I did a couple of minutes ago where I had a 2 node and a 3 node, I should have rearranged them in this order instead, because more of my nodes are leaning down to this side, so it makes sense to try and keep more of my keys over there. In any event, once I do that double rotation, I've filled in the missing space with a key, and what I have left on the left is a 3 node. So I've got this red node over here because now there are 2 keys over on this side. But if I look at the black balance constraint, everything seems to hold up. In fact, actually, this being a red node, I can just look at this and observe that all of my leaves are at the same actual depth of the tree and everything above them is black. So what I did there was equivalent to restructuring, rearranging a subtree by simply splitting the parent and splitting keys amongst the children. There could be more than one way of doing this. As we observed, there actually is a way I could have done it which I drew out, which resulted in the 3 node being on the right, and that's fine. Just like with 2-3 trees, any removal operation that satisfies all the constraints when you're done and has log n running time is valid as far as I'm concerned. But the way I chose to do it was with a double rotation. All right, what about removing 8? Okay, so this now, you can see the diagram is zoomed out a bit, implying that we're going to have to do some complicated stuff. Okay, so there's 8. I just deleted it. And I noticed that it's a bit sparser of a setting than it was a minute ago. So I'm inside of a family that's pretty small. I've got 3 nodes and only 2 keys. And we know this was the deletion case in 2-3 trees that was the hardest one to deal with. There isn't enough available inside of this family to redistribute. So I'm going to have to basically push the problem upwards in the tree. So I've got this gray node whose parent is a 2 node, and its sibling is also a 2 node, and so there's no easy way of rearranging keys locally. What we did in a 2-3 tree to solve this problem was say, well, all things considered, it's clear we can't solve the problem down here, so why don't I try and push the problem upwards? And I also have to make sure that my leaf depth constraint is met, so what I'll do is I'll put 5 and 6, the 2 remaining keys in the family, into a 3 node, and I'll make the gray node, the 1 node, the parent of that. And then it becomes one of the children of 17. And that way, hopefully, we can solve the problem up at the root. So I do that. I end up with this situation. Now, this is something that can't easily be modeled in a binary tree. So over here, we had this notation we made up last time to refer to this case. I don't really know how to draw that with the gray node. I'm not really comfortable drawing it having only one child like this, because in a binary tree, things have either a left child or a right child or both. So what I've chosen to do is draw the gray node as having as its left child the remaining 3 node. And the gray node just has no right child, which obviously is a problem, but the existence of the gray node is a problem to begin with. Okay, so I've done this. I've now pushed the gray node up by 1 level. And so now, hopefully, I can find some way of solving the problem here. Now, if we stare at this, we realize it's actually the same problem again. So what I have to do is repeat the same thing. This is another instance of the same 2-3 tree removal case, where what I have to do is to combine the 17 and 58 into a 3 node, and then the 3 subtrees would be these 3 subtrees here, and then I just push the problem up 1 more level. Okay, so I can't solve the problem at the level it's at, so I go up further. I end up with this situation. And we can recall from the previous lecture that the solution in the 2-3 tree to this case is, you've managed to push an empty space up to be the root of the tree. But that's easy to fix. We just delete it. The empty space is now gone. None of the constraints get violated by fully deleting the node here, because all the constraints, everything in the tree that moves as a result of deleting that moves equally. That is, all of the leaves of my 2-3 tree now move up 1 level. So the leaf depth constraint is still met. And the same is true of my red-black tree. So formally, the gray node is a black node that's fallen into disrepair. So if I evaluate the black balance constraint at this point in the tree, what's the black depth of 71? Okay, so I do 1, 2, 3 black nodes. And then from 6, 1, 2, 3 black nodes. What about from 20? Okay, so there's 1 black node, 2, 3 black nodes. However, if I delete this node, if I'm counting this node as a black node and I delete it, notice that every node's black depth goes down by 1. So the black depth constraint is still met. I still have perfect black balance. By moving the problem to the root of the tree, it's true that some of the depths and whatever change, but every depth changes by the same amount. Every node is affected equally, so I can justify that deletion. And so I have to also do other modifications to make this work, so I actually I got a little bit ahead of myself there. Before I can delete this, I do still have to rearrange the underlying red-black tree to be compliant. So what I would normally do, and the reason I'm doing it in this order, is because the deletion of the gray node happens at a higher level. So before I go to a higher level, before I recurse upwards, I should fix whatever's happening at the lowest level. So I'm going to actually just scroll back 1 step. So here is the step where I push the gray node upwards, and I ended up with this tree here. Before I recurse upwards to the gray node, I do have to bring this tree into compliance with all the other constraints. And currently it isn't, because I've got a 58, which is a red node that's the right child of 17. So before I recurse upwards, I have to perform, in this case it's going to be a rotation, I have to make it so that this 3 node here is in the correct orientation. Because I'm allowed to have this 3 node, but I'm required for this 3 node to have the largest key at the top and the red child being on the left. Okay, so anyway, what I do now is I perform a left rotation about 17, and I do the color fix-up so that 17 is now red. And now I have on this side, this is now a fully compliant red-black tree. So now I can recurse upwards and dispose of the gray node. And similarly, this is where I would now recurse in the 2-3 tree to figure out what to do with the gray node. So because the gray node is the root of the tree, I can delete it entirely. I've already explained why I think that that makes sense. Before I go forward though, so I now have a fully compliant red-black tree again. I've finished my restructuring operation. It does match up with this 2-3 tree. I want to quickly observe something about the position of that gray node in the middle of this. So consider this case here. In the 2-3 tree, we know better than to just go delete the gray node. So we saw in the previous lecture that because of the way the tree works, the gray node can't just be spliced out. And so maybe we know that we can't do that in the red-black tree either. But suppose you didn't see this. If you see this configuration and you're told, fix the tree, doesn't it seem tempting to simply just delete that? It's a node with one child, so you could just stitch the tree back together without that there. But that won't work, and the reason it won't work is the black balance constraint. So suppose I start at the 6, and I say, what is the black depth of 6? Well, how many black nodes do I encounter? Remember that the gray node does count as a black node, so I encounter 1, 2, 3 black nodes. If I look at the 34, I encounter 1, 2, 3 black nodes. If I look at the 20, I encounter 1, 2, 3 black nodes. If I were to simply splice out the empty space and make the 6 directly the child of 17, the black balance constraint would not be satisfied. Because now if I start at the 6, I encounter 1, 2 black nodes. But I still see 3 if I go up from 34. That is why I had no choice but to keep pushing the gray node upwards. Because the gray node is not at a position in the tree that can be sacrificed. That position is critical to the tree at this point. Notice that, and the slides point this out, I actually made this mistake, even though I made a slide to specifically observe that I shouldn't make this mistake. What I did was I talked about deleting the gray node too soon. So I will have to, by way of an apology for that, what I did was, when we got to this step here, I just went on about, because, you know, the gray node is the most exciting thing here. We all think the gray node is the most fascinating aspect of this example. I went on about how we could delete the gray node, but I forgot that the thing below it hadn't yet been fully restored. And so I forgot that we had to do this step in the meantime. And the slide points that out. It says, yeah, look, you're probably obsessed with that gray node, and you could have deleted it first and then gone down and fixed up the tree below it, but that isn't the way it would typically work if you're doing it recursively. So recursively, you walk upwards in the tree. You don't touch that gray node until you are completely done below it. So until you've completely finished whatever you were doing down here, you don't bother figuring out what's happening up above. So sorry about that. That's my human brain and not something the computer would do when you wrote code to work recursively. Okay, let's continue with our sequence of removals. We have now discussed the most unpleasant removal situation, which is where an empty space percolates all the way up to the top of the tree, but we still have to clean up a couple of other cases. So one of them is, what about removal of an internal node? From 2-3 trees, maybe you see what's coming here, which is that we basically do the same thing we do in a typical binary search tree, which is that if we're removing the key 17, that would be the root, we just cross it off and then fill it with something from nearby, and then hopefully, recurse down the tree to figure out what to do about that. So I'll show off how we do that. So let's remove 17. Okay, well, the first step is go find the key you're removing and then delete it. There we go. Now the root is empty, and we obviously can't have that. We need to fill that with something. So here, what we do is, because I have been following this convention, I will continue. We fill that, we go find the maximum key in the left subtree, and then we just bring that up, and that fills the gap. We could also use the minimum key in the right subtree, and there are good reasons why we actually should be doing that here. But I won't, because I want to be consistent with my own rules up until this point. There's no asymptotic reason why we have to do it either way, but there is a sort of heuristic reason why it can be clever to always use the minimum node in the right subtree, and that's this. Suppose the tree looked like this. I deleted 17, so suppose there was a 19 down here. The minimum key in the right subtree could be a red node. It'll never be a red node if I look at the maximum key in the left subtree, because the maximum key in the left subtree has to be the right child of something. And that means that the maximum key in the left subtree has to be a black node, whereas the minimum key in the right subtree could be a red node. Maybe it won't. In this example, it wasn't. I mean, the minimum key was 20. But if it was a red node, then, and I bring the red node's value up, then maybe removing the red node is really easy. And so that is one heuristic reason, like if you're lucky, and maybe you are lucky sometimes, that is one reason why you might want to always use the minimum key in the right subtree, because occasionally you get this lucky case where you can remove very easily. It doesn't hurt anything asymptotically to do it either way, and so for the sake of consistency, I'm not doing it here, but keep that in mind. That is a sort of, a good rule of thumb to follow. Okay, so I move the key 10, the maximum key of the left subtree, all the way up into the root, and then I copy it into the empty node. And then what I'm basically doing here is I recursively try and delete the key 10 from here. So I've skipped a step and just cleared out that node to begin with. And now I have to do the same restructuring I would do if I deleted 10 from this position. All right, so just like in any other tree that we've worked with, 2-3 trees, binary search trees, ultimately when I remove from an internal node, maybe over multiple steps, but I eventually end up deleting something from a leaf, and then I work my way back up from the leaf as I would in any other removal. And so we can now handle this the way we would handle any other removal. So in this case, what I could do is observe that I have the case where I've got in the immediate family enough keys to spare, and I could solve this by bringing the 8 down and bringing the 6 up. And that could be done with a rotation. So I could rotate right about 8, and I get this situation here. This is the slide observing that in general, you actually might want to always go with the minimum key in the right subtree. But it actually doesn't make much of a difference either way. But heuristically, why not save the time if you can? So there's my right rotation, and now the tree has been restored. So as with insertion, I can actually give you a list of all the removal cases. In general, the easiest removal case is removing from a 3-node leaf, because in that case, all you have to do is delete a red node and maybe you may have to perform some rotation, but that's pretty much it, a very local operation. In all other cases, other than the case where you are deleting one of the keys from a 3-node leaf, you end up creating a gray node that has to get moved around somehow until it can be resolved. And remember that the gray node is a black node that cannot currently do its job. So it's a black node in disrepair, which means although it's empty and will eventually be eliminated, we have to treat it as a black node as long as it's part of the tree. Even if we rotate it around somewhere, it's still subject to the perfect black balance constraint. So any adjustment we do must be absolutely certain to maintain that constraint. And even I, while writing my own code for red-black trees and making these slides, accidentally violated that a couple of times and had to go back and fix it. Because there are times when you're designing the set of rearrangements to make, because I've observed before, there are multiple ways to implement removal. There are different cases that you could implement differently than I do and still work. Because there are multiple cases, as you go to work out each case, you have to use what you know about the situation to figure out which sequence of rotations to perform. But remember, keep that black balance constraint in mind, because that must be obeyed, or else we don't get any guarantees about the height of the tree. So what I'm going to do is, to make that absolutely clear, in the diagrams in this section, I'm going to label each node with its current black depth, and I'm going to start counting at 1. So that is the root of a subtree, it has a black depth of 1. I know that normally in trees we count depth based starting at 0, which is a good idea and I like it. But for this one case, because we've got so much else to worry about, it makes sense to use a more natural counting protocol where we just count starting at 1. So what I've done is I've labeled each thing with its black depth. And just like before, these nodes T1, T2, T3, T4 are placeholders for some arbitrary subtree, which could be very large or it could be empty. What we need is for every removal operation restructuring that we do, for each of the T's, because each of these subtrees T to end up at the same depth leaving as they did going in. So if T1 is at black depth 2 at the beginning of my operation, then when I'm done, T1 has to also have black depth 2, because that guarantees us that any leaves that are down at the bottom of T1 have the same black depth that they had before. So any restructuring I do must preserve the black depth of every each one of the T's that I have, these arbitrary subtrees. I'm under no obligation for, let's say, K1 to be at the same black depth as before, because the black balance constraint only applies to leaves. It is a way of phrasing the leaf depth constraint from 2-3 trees. And so remember that in any removal operation, we have to guarantee that the arbitrary subtrees have the same black depth when I'm done as they did when I started. And that gray nodes count as black nodes. So notice how this gray node has a black depth of 2, because counting itself, it is at black depth 2 from the root of the subtree K3. All right. Yeah, and then as I said earlier, that means basically the restructuring operations we do either must ensure that all nodes have the same black depth, all of the subtrees, or if black depth decreases, that it decreases for every node in the entire tree, not just in this subtree, every node in the entire tree. And that can only happen in the case where we push a gray node all the way up to a root and then delete it, at which point the black depth of everything in the tree goes down by 1. Okay, case 1. Suppose that you delete the key in a red leaf. So you have an empty red leaf. That is equivalent to if you have a node like this, K1, K2, a 3-node leaf, and you delete one of its keys. And all we do then is condense the node down to a 2-node. In the event that the key you deleted was in the red node, all you do is delete the red node, and we're done. That's it. So that's the easy deletion case. All right, case 2. Suppose you are in a 3-node leaf and you delete the larger of the 2 keys. So now you have an empty black leaf with a red left child. Now I guess it's not really a black leaf because it does have a child. I mean that the complete 3-node together comprises a leaf. So in this case, all you do is you move, well, you could call this a rotation, I don't know. You move K1 up into this, and then you delete the red leaf. Or alternatively, you could rotate around the empty space so that K1 comes up and the empty space goes down, and then delete the empty space, whatever. In any event, you end up with a single black leaf. Okay, so that's case 2. That's also a pretty easy case. Okay, now we have to get into the weeds. So case number 3. So this is all from the point of view of the root of your subtree. So when you're looking at this node and you check for case 3, what you're asking is my left child, so if I go left twice, is it a gray node? So here, from below, a gray node has shown up if I go left twice. And the question is, how do I resolve this? Remember that the subtrees T1, T2, and T3 might be empty. It doesn't say T4, you'll notice, and that's because it does seem as if T4 has to contain something because there is something down below K3 on the other side. And remember that in a 2-3 tree, if there are non-trivial children in 2 positions, there must be a child in the 3rd one. But T1, T2, and T3 could be empty. So what do I do in this case? What I need is to ensure that the black depth of each of these things is preserved. And notice that, and I'll show on the right-hand side, notice that actually has been the case in the operation I performed. So if I look at the black depth of T3 now, it's 1, 2, and at the end it is 1, 2. It's still 2. And whereas T1 and T2 similarly, because the red node gets ignored, T1's black depth was 1, 2, 3, and when I'm done, or wait, hold on a second, that is... Okay, sorry, the T1's black depth was 1, 2, 3, and then when I'm done, T1's black depth is still 1, 2, 3. And so that's important, and that's why we can't just splice out that gray node. It counts towards the perfect black balance constraint. I think it might have been on this case originally that my slide had a mistake that I had to go back and fix because I had forgotten about that, and you even heard I stumbled there because I'm now second-guessing myself. Anyway, the remedy that we have to use in this case is we rotate this way, so we have to keep T1 down pretty low in the tree. That basically is our concern. We're allowed to move T2 and T3 upwards a little bit if we need to, as long as we do so by moving a red node down. Because, of course, their black depth doesn't change if this red node gets out of the way and they move up. And that's what I've done here. So T3 is actually moved up a little bit. But since the thing that got out of the way was red, the black depth of T3 is exactly the same as it was before. And so what I've done is I've just rotated left about K1, I guess. In this case, the gray node vanishes. The reason the gray node vanishes is because what I'm doing here, we saw an earlier example of removal where this happened. I'm just redistributing keys, essentially. Okay, so now what about the sort of symmetric case where your left-right child is a gray node? So from the point of view of K3, if you go left and then you go right, you have a gray node there. And the gray node only has one child, so a subtree T3. As before, T4 can't be empty, but T1, T2, and T3 might be empty. And so this is handled pretty much the same way as before. So my biggest priority is I have to keep the black depth of everything the same. And T3's black depth, if I count it, it's 1, 2, 3. The gray node counts. So that sort of forces me, basically, like if I get rid of the gray node and T3 moves up, I sort of need that the parent of T3 has to be a black node so that the black depth is the same as when I started. On the other hand, if I make this node black, well, then T2 and T1 now have a higher black depth. And by process of elimination, it sort of becomes clear that maybe I can solve the problem by simply transposing the locations of this black node and this red node. If this node becomes black, this node sort of has to become red. And so I do that. And what I'm doing here, if we model this, it would be nice to draw this in terms of the 2-3 tree, but I don't have space for that diagram. But basically, this does correspond to a very familiar 2-3 tree deletion case. And it is just the movement of the red node just corresponds to shuffling keys around between two different 3 nodes. All right, so now suppose that I'm sitting here and my right child is gray. So I am in a 3 node because my left child is red, but my right child is gray. So what I'm doing here is, this corresponds to a 3 node leaf. I think this might be a typo. Let's just disregard this statement. I think that might have been copied and pasted incorrectly. Okay, so what I have, and this is again only difficult because of the perfect black balance constraint. So what I would like to do is just make T4 the right child of K3, but I can't because this gray node, which does count as a black node, means that T4 has a black depth of 3. And so I can't just splice it in because that would decrease its black depth. So what I sort of have to do here is I've got this 3 node, and what I need to do is to move some keys over to repopulate this side of the tree to keep the depth of T4 the way it was. And so that's what motivates this. Now, what I can do here is temporarily, I can just make T4 the child of K3, but I have to then move K3 downwards a little bit. So you can see in these directions, just to get rid of that gray node, I make T4 the right child of K3, and then I rotate around K3 to push K3 down a bit. And as a result of the rotation, it says I do a bit of recoloring here. When I'm done with this rotation, K1 becomes the root, and K2, the subtree of K2, then becomes the left subtree of K3. So I end up with this. K1 goes up, and it becomes the parent. So I'll just draw the rotation as I do it here. K1 becomes the parent of K3. Its left subtree is still T1. Because I make K1 black, by the time I'm done all of this, I can observe that the black depth of all of my subtrees is still the same. It's just quite involved to come to this modification. So I'll notice the black depth, we'll just count it off. The black depth of T1 is 2 here, it's 2 here. The black depth of T2 is 3. And it's still 3 here. Same thing with T3, and then same thing with T4. And you'll find, as I mentioned, because as I said, like in my own code and in my slides, I've had to make a couple of corrections over time because I've noticed errors where I've forgotten about that. Often when you're coming up with the exact sequence of rotations to perform for removal, all you have to do is consider options until you know that the depth has to remain the same, so you just find whichever option keeps the subtrees in the right order and the depth the same. So you can reverse engineer it if you need to. And I should add, going back to what I said at the very beginning of the lecture about how when I learned topics like this, about balanced search trees, often all I was given was slides like this. I was told, if you have this, you get that. I wasn't even told what a gray node was. It was just, if you have this, you get that. And if you don't understand it, then maybe you're just not good enough. So we need to have slides like this because it's good to have a recipe. When you actually go to write code for red-black trees, knowing if you have this, you do this is useful. But you always know that if you want to understand why we have this or why it works, you know the conversion, you know how to turn this into a 2-3 tree and how to view it, and you know what constraints are in play. So if you ever wonder, why do we do it this strange way, you have a way of generating an explanation. And so recipes are nice, but we're not computers, right? Recipes are good for computers. A computer just wants to know which case translates into which output. But for us as people that understand this, it isn't enough to just get the recipe and be able to reverse engineer why it works. All right, so case 6, I think this is the last case. What if we have the situation where our left child is gray and the right child is black? So we are in a 2 node where one of our children is a 1 node, basically, in 2-3 terms. And observe that if we think about this as a 2-3 tree, this does correspond to the most unpleasant 2-3 tree removal case where we can't fill in the missing keys with other members of the immediate family. And the solution in that case, of course, is to push the problem upwards in the tree. So we end up with this, and these diagrams, as I said, are a bit awkward because the gray node sort of has a left child only. But ultimately what we're doing is we're combining, so we have this situation here, if I use the 2-3 tree notation. So I've got K1, K2, and the empty space. What I do, my remedy, is I put K1 and K2 into a 3 node, There it is. And then I propel the empty space upwards in the hopes that somebody else can fix it. Now, if it gets pushed all the way to becoming the root, then the fix is just to delete it. But it could end up being pushed upwards, and it could end up just being the child of some other node. Who knows? We just recurse upwards to fix it. Okay, so to do that, we can describe that in natural red-black terminology, but we're achieving this effect. We want the new root to be the gray node, and we want to push everything else down below it, and then have K1 and K2 become a 3 node. And so for K1 and K2 to become a 3 node, because K1 is obviously less than K2, K1 has to become the red left child of K2. T1, which has currently black depth 1, 2, 3, becomes the left child of K1, which then still has black depth 1, 2, 3. Everything still looks good. T2 becomes the right child of K1, and T3 remains the right child of K2. In terms of the rotations, or how we do that, so one option would be to I don't really want to model what happens with this gray node in terms of a rotation. You could claim that what's really happening here is a certain weird degenerate rotation involving the gray node, because I don't want to think about rotations with nodes that only have one child like this or can't have 2 children. Instead, I just say, look, move the parent to be the top position. We know what we're trying to achieve with this. Then make T1 the left child of K1, and then we just do the rotation with what's left. So in other words, what I've said is splice this out, make T1 the left child of K1, then rotate, and that gives us this. And then I make K1 red to accommodate the fact that it's now a 3 node. And finally, I recurse upwards because this gray node could now be the child of something else, which could make it somebody else's problem. I could be back in case 6, or I could be back in case 5, or case 4, or case 3. This gray node could have come up from below in all of these cases. Oh, there's a case 7. Okay, fine. In the case 7, so here I have the left child is gray and the right child is black. What about the symmetric mirror image, I guess, where the left child is black and the right child is gray? Well, okay, let me look at the outcome. We want the same thing. So I'm not going to spend too much time on this. This is ultimately the same issue as before. It's just the mirror image because the gray node is so weird that it's useful to have a separate recipe for the mirror image. In this case, though, the effect is the same. K1 and K2 both together become a 3 node. You can see there's the 3 node there. And the subtrees pretty much appear where you expect them to. That is, T3 becomes the left subtree of the 3 node, T2 becomes the middle one, T1 becomes the left one. I think actually maybe this case is a little bit easier to handle than case 6. In any event, once we're done, the gray node is up at the top and we recurse upwards. In the event the gray node is now the root of the tree, we can simply delete the gray node altogether. So what do we know? Well, red-black trees are efficient and streamlined, and they are really, really interesting. So we've been able to take all of this sort of clunky logic of the 2-3 tree. A 2-3 tree is a really beautiful thing on paper. Like, it really makes sense what we're supposed to do with a 2-3 tree if we look at it on paper. But in code, implementation-wise, it's rather clunky. There are lots of different cases to throw around, lots of different types of nodes, lots of different if statements we have to write. We found a way of taking that logic and incorporating it directly onto the logic of a binary search tree. Notice that the insertion and removal procedures for the red-black tree began with ordinary binary search tree insertion and removal, and then did a restructuring step afterwards. In other words, really what a red-black tree is doing is it's using a binary search tree, performing the regular binary search tree operations, and then proactively fixing any imbalance that's created. Whereas a 2-3 tree fundamentally is just designed in such a way that imbalances are impossible. And so we found a way to convert, even though both of those questions seemed difficult to answer back 2 lectures ago when I said we have a fork in the road. Either we find a way of making a tree that can never become unbalanced, or we find a way of quickly fixing imbalances as they occur. We found a way to do both of those things and then showed that in fact they're the same method. A 2-3 tree and a red-black tree are the same thing. They're just the same thing that has been represented a little bit differently. And if we represent it in one way, we get a tree that can never become unbalanced. If we represent it the other way, we get a tree where imbalances can be fixed efficiently. And moreover, the 2-3 tree operations, once we think about them in terms of the red-black tree, are really streamlined. Whereas previously, to split a 4 node, we have to do a whole bunch of juggling with nodes. In a red-black tree, we just flip some colors. That's amazing. And once I finally figured out what red-black trees were, which was long after I took an algorithms course, I actually sort of felt like I'd been shortchanged a bit. I had spent years sort of in fear of having to implement red-black trees because I really didn't know what was going on, because all I had ever been shown was, here are some red nodes, here are some black nodes, here's how you do a rotation, now memorize a bunch of details. Instead of, here is a process, an orderly procedure that actually is pretty natural for making sure the tree is balanced, and here is how we can map that on to the familiar binary search tree stuff that we're used to. So I hope that this lecture was a step in the right direction as far as presenting the red-black tree as a logical thing, a thing that we can actually understand intuitively, rather than just a set of rules to be followed. Because it's important, I think, that we understand that algorithms are designed not just for computers, but for people. It's important that we design algorithms and describe them in a way that people can understand. And if we ever find ourselves in a position where we have to say, here's something complicated, I hope you get it, memorize it, and you understand it yourself, because if you can't get it on your own, you're just not good enough. That doesn't make any sense. That isn't the way the world works. Being able to convince somebody else that something works is a sign of the intelligence, not expecting somebody else just to get everything from scratch. It is maybe impressive if people can figure something out from scratch without an explanation, but you're not doing a good job of explaining something if the person you're explaining to doesn't understand it. And as an algorithm designer, that is your job. You have to prove your algorithm works. You have to justify why the operations work the way they do. So because red-black trees are basically just a special binary search tree, they're a binary search tree with a bit of extra machinery, but none of that machinery gets in the way of the basic binary search tree operations, we really do get to have our cake and eat it too. So yes, the insertion and removal operations do require some extra work because we have to do that restructuring of the red-black tree. We've seen already that it is pretty streamlined. We only do rotations and color flips, and we work our way up the tree, but yes, there is extra work. But what's really great about the red-black tree is that deep down, we can treat it like it is a regular binary search tree when it counts. When I want to do the find operation, I can run exactly the same algorithm on my red-black tree as I run on a binary search tree, exactly the same. The binary search tree search algorithm doesn't care about the color of each node, doesn't care about any of that stuff. I'm able to use the default, ordinary, basic, streamlined binary search tree search algorithm on my red-black tree with no modification. All of the extra machinery falls into insertion and removal. And way back at the beginning, when I started talking about the dictionary abstract data type, I said that is my goal. I'm okay with doing a bit of extra work on insertion and removal. I want find to be as fast as possible. And so we've actually achieved that with red-black trees. We have the best of all worlds. And as I mentioned at the very beginning, as of 2025, it does appear that if you go looking in the standard library for your favorite programming language, although not Python, as I mentioned in the last lecture, Python dictionaries are not implemented with a search tree. They are not comparable-based dictionaries. They are, in fact, something else, something we'll talk about in the next lecture. If you go look, though, at self-balancing search tree implementations in the standard libraries of your favorite language, I will bet that you discover that they are red-black trees. They may not be exactly the same as ours. They may not be left-leaning red-black trees, but I'll bet you could understand them. I'm not saying you should go read the code necessarily, because standard library code can be pretty nasty looking sometimes. But if you're presented with a red-black tree, for example, where we're allowed to have 2 red children on a node, I hope that you now have the tools to be able to understand what to do with those cases. And it doesn't really take that much to generalize our operations to situations where that case is allowed. In other words, if you're allowed to have 4 nodes like this, then it actually makes your life easier. You just leave them there instead of splitting them. Although you do still have to worry about like what happens if you get a 5 node or something like that. So as of 2025, there is still evidence that red-black trees are the dominant form of self-balancing search trees. And that's one of the reasons why I chose to cover it versus some other implementation of a self-balancing tree. If we had covered AVL trees, we would have spent a lot less time talking about the specifics of individual operations, but a lot more time, I guess, writing proofs, because AVL trees don't descend. Unlike red-black trees, we can't rely on all these 2-3 tree results that we were able to use today. So there we are. There's our study of binary search trees. We're not done talking about dictionaries, though, because this elephant in the room for the last few lectures has been, hey, if dictionaries are so great, and if Python dictionaries are such a big deal, then exactly how do Python dictionaries work? And so there's a data structure we're going to have to cover to explain, to fill in that gap. What if I want to write a dictionary that isn't based on a comparable framework?